Take a look at this picture. This is Eugene Cernan, the last astronaut of the Apollo program to step on the moon, but something is strange here. Do you notice? The night sky looks completely devoid of stars. All the photos taken during the Apollo missions show a sky completely devoid of stars, even though the universe is full of billions of stars. The Apollo astronauts reported that they could not see any stars from the moon. This absence of stars has given rise to many conspiracy theories for years. Some even claim that it is proof that the moon landing was fake, but the real explanation is much more fascinating and profound than any conspiracy theory. Why is space so dark? The German astronomer Johannes Kepler first posed this problem in 1610. Our galaxy, the Milky Way, is so vast that it is believed to have between 100 and 400 billion stars. In addition, it is estimated that the observable universe alone contains billions of galaxies containing billions or sextillions of stars. Given this, astronomers wondered why, since the universe is full of countless stars in all directions, shouldn't it be bright and full of light? Surprisingly, it is not, and this has baffled astronomers for centuries. Careful studies suggest that the sky should be as bright as the surface of the sun, but when we look up at night, we mostly see darkness. This enigma, known as Olbers' paradox, took almost 300 years to resolve. Olbers' paradox comes from the steady-state theory. Imagine a universe in which everything has always been the same and always will be, for example, the position of the stars, the galaxies, everything. This was the central idea of the steady-state theory, which was once the main explanation for the universe. According to this theory, the universe was infinite, without beginning or end, uniform in all directions, and did not expand. With this theory in mind, astronomers faced a question: why is the night dark if the universe has always existed and is full of stars? Then shouldn't the entire night sky be as bright as the sun? According to the steady-state theory, even the light from the most distant stars should have reached us already, illuminating the sky with its combined glow. One of the first explanations suggested that perhaps the stars were simply too far away to affect our night sky, but this idea did not work with the steady-state model. If the universe is infinitely old, there would have been plenty of time for the light from any star to reach Earth, no matter if that star is on the edge of the universe. This light should fill the sky, leaving no dark spots. Johannes Kepler had a different idea to solve the paradox, which went against the steady-state theory. He suggested that the universe was not infinite after all, but that the stars only extended to a certain limit, and beyond that, there was only empty space. This idea was interesting but raised big questions: how far does this space with stars go, and what is beyond that limit? Kepler's idea of a limited universe also had its own problems. If the universe had a limit, the combined gravity of all the stars and planets could potentially pull everything back towards the center, causing the universe to collapse. Due to these challenges, most astronomers continued to believe that the universe was infinite. This meant that the paradox and the idea of a stable universe remained unresolved for almost 200 years. Then, a famous German astronomer named Heinrich Olbers again drew attention to this old question, asking again why the night sky is dark. Since then, Olbers' name has become closely linked to the paradox. In his time, people still believed that the universe was unchanging. Olbers suggested a simple idea: if the universe is infinite, it would be full of dust and rocks. These particles could block the light from distant stars, making them appear dimmer to us. This cosmic dust and rocks absorb and block starlight as they move through space. Today, many people still think like this, comparing it to how clouds block sunlight and darken the sky. Like clouds, cosmic dust and rocks can hide starlight. However, Olbers' explanation was not complete. Over time, the dust and rocks that blocked the light would heat up and begin to shine on their own. This means that the universe would still be full of light, just like before. Dust and rocks only temporarily hide starlight before releasing it again, so the total amount of light that reaches us would still be the same. So, what really solves this paradox? It took another 100 years to find the real answer. In 1929, Edwin Hubble used his powerful telescope in the hope of finding signs that the universe was shrinking, which would support the idea of a finite universe, as Kepler suggested, but instead, Hubble discovered that the galaxies were moving away from us and that the farther away a galaxy was, the faster it seemed to move. This showed that the universe was not staying the same or collapsing, but was actually expanding. This discovery led to a new question: what does an expanding universe mean for its origin? Scientists now think that the universe began as something incredibly small and dense, and then expanded very rapidly, a process called cosmic inflation. As it expanded, it cooled, and eventually, stars and galaxies began to form. This understanding helped develop what we now call the Big Bang theory. Scientists believe that everything began about 138 billion years ago and is currently our best explanation of how our universe began. Today, most scientists agree that the universe is about 138 billion years old. When we look at light that is 13,800 million years old, we do not see stars, not because the light has not reached us, but because we are looking back to an era when stars did not yet exist. The further we look into space, the further back in time we see, until we reach what appears to be the edge of the universe. It is not a real edge, but the oldest light that we can see, known as the cosmic microwave background. It is the residual glow from the Big Bang. When we use telescopes to look beyond the first stars, we see a special kind of light. It is not light from the stars but light that remained from the Big Bang, forming a kind of background glow. Beyond where the stars are, however, the Big Bang theory raises a new question. It suggests that the universe used to be much brighter, especially during an era called the era of recombination. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow of the Big Bang, known as cosmic background radiation, should be very bright. According to Olber's paradox, this bright background should make it difficult for us to see faint stars in the night sky. Since the Big Bang occurred 13,800 million years ago, the universe has followed three main rules as it grows and changes. First, at the beginning, the universe was extremely small, very dense, and super hot. Second, only a fraction of a second after its start, the universe began to get bigger and colder. Third, and this is really important, the universe will continue to expand and cool. Astronomers believe that this will continue until the universe becomes so cold that all heat disappears. This is called the thermal death of the universe, sometimes also known as the Great Freeze. In this future scenario, the universe has expanded so much that it has completely cooled, and all thermal energy has disappeared. All these rules show us that our universe has been getting bigger for the last 13,800 million years. When the universe began, it was full of very bright, hot light. As the universe expanded, this light stretched. This stretching has converted the light into longer wavelengths, which means it is colder and less bright than before. This is what we call the redshift effect. It is the reason why cosmic background radiation is not extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expansion of the universe solved the ancient paradox of the universe that began at a single point and grew rapidly during the Big Bang. For billions of years it has cooled because the universe is not infinitely old, there is a limit to how far we can see into space. The redshift effect also makes the light from distant objects appear fainter. These combined factors give us the dark sky that we see today. The fact that the night sky is dark shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe began with the Big Bang and has been expanding since. The night sky is like a quiet reminder of how the universe began as a very hot and dense place. This vision helps solve Olber's paradox and also makes us appreciate how incredible and complex the universe really is. One of the main theories of modern cosmology is the Big Bang theory, which explains how our observable universe was born. It describes the origin and the evolution of the universe. Imagine all the stars, planets, and galaxies compressed into an incredibly hot and dense point. Scientists believe that this is how everything began about 13,800 million years ago. Since then, the universe has been expanding and cooling. This small point exploded in an event called the Big Bang. From that moment, the universe began to expand and cool. But how do we know this happened? The Big Bang theory is supported by much evidence. A key piece is the cosmic microwave background radiation, which is a residual glow from the early universe. This radiation gives us a picture of the universe only 380,000 years after the Big Bang. Before that, the universe was so hot and dense that we could not take pictures. This radiation was discovered by accident in 1965 by Arno Penzias and Robert Wilson. Another important discovery is the redshift of galaxies, which means that galaxies are moving away from us, showing that the universe expands and grows, it does not slow down. This was first observed by Edwin Hubble in the 1920s. The further away a galaxy is, the faster it seems to be moving away from us, which supports the idea that the universe was once much smaller, hotter, and denser. The Big Bang theory also explains the amounts of light elements, such as hydrogen, helium, and lithium, in the universe. These elements were formed in the first minutes after the Big Bang, when the universe cooled enough for protons and neutrons to form nuclei. But the Big Bang theory also raises some big questions. For example, it does not explain what happened before the Big Bang or what is beyond the part of the universe that we can see. It also introduces the idea of cosmic inflation, which is a rapid expansion that occurred just after the Big Bang. This helps solve some problems of the theory and coincides with what we observe in the cosmic microwave background radiation. Before the discovery of cosmic microwave background radiation, there was a popular idea known as the steady-state theory. This theory suggested that the universe has no beginning or end but remains the same as a whole, although it expands constantly, creating new matter. This theory was popular in the decade of 1940, but it lost support when scientists discovered the cosmic background radiation in 1965, which firmly supports the Big Bang theory. In addition, theories such as the cyclic model continue to be explored and developed, which suggests that the universe goes through endless cycles of expansion and contraction, which continue to be explored and developed, adding richness and diversity to our understanding of cosmic origins. After the Big Bang, the universe expanded and cooled. At the beginning, it was a hot, dense soup of particles that, as it expanded, cooled, allowing the particles to join and form the first atoms. These atoms then formed the first stars and galaxies. The expansion of the universe continues today, with galaxies moving away from us in all directions. Let's think even further back. The first particles of any kind were protons and neutrons, which together form the atomic nucleus. These appeared around 0.00011 seconds after the Big Bang. Before that, there really was no material as we know it, but physics allows us to go back even further in time to processes that took place before stable matter existed. This leads us to the Grand Unified Epoch. At this point, we are in the realm of speculative physics, since we cannot create enough energy in our experiments to study the processes that occurred then. However, a plausible idea is that the universe was full of a soup of hot particles, including quarks, which are the basic components of protons and neutrons. There were approximately equal quantities of matter and antimatter. Each type of matter particle, such as a quark, has an antimatter counterpart that is almost identical, but with a key difference. When matter and antimatter meet, they destroy each other in a flash of energy, which means that these particles are constantly created and destroyed. But how did these particles come into existence in the first place? If we think in terms of quantum fields, it tells us that even a vacuum, which we consider empty space, is full of physical activity in the form of energy fluctuations. These fluctuations can cause particles to appear and disappear shortly thereafter. This may sound strange, but such particles have been observed in many experiments. The vacuum of space is full of particles constantly created and destroyed, apparently out of nowhere. However, this suggests that the quantum vacuum is actually something rather than nothing. Suppose we wonder where spacetime comes from. To answer this, we have to go back to the beginning, to the Planck era. This period was so early in the universe's history that our best theories of physics no longer work. It occurred only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Physicists generally use quantum mechanics for tiny particles and general relativity for large cosmic scales, but to understand the Planck era, we need a complete theory of quantum gravity that combines both. We still do not have a perfect theory of quantum gravity, but there are ideas like string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper, microscopic processes. What we experience as space and time results from quantum processes that, at present, do not make much sense to us because we are used to the large-scale world. Quantum fluctuations occur constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can arise from the vacuum, exist for a moment, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone do not explain the enormous scale and complexity of the universe. There is dark energy, a mysterious force that fills all space and accelerates the expansion of the universe. Although we do not fully understand dark energy, it is believed to play a crucial role in the creation and evolution of the cosmos. So how did we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, laying the foundation for the formation of galaxies, stars, and planets in the early universe. Our usual understanding of space, time, and cause and effect falls apart. Despite this, all candidate theories of quantum gravity describe something physical that occurs in the early universe, some quantum precursor of ordinary space and time, but where did it come from? Even if causality does not work in the usual way, it could still be possible to explain parts of the early universe in terms of other parts. Unfortunately, our best physics still cannot give clear answers. Until we develop a theory of everything, we will not be able to give a definitive answer. The most we can confidently say is that physics has not found any confirmed case of something arising from nothing. When we look around us, everything we see is made of matter, everything that touches, sees, and interacts is composed of tiny particles. For billions of years, these particles have come together to form galaxies and stars. They all follow the same physical laws and exist within the same space. Space-time framework. But there was a time when the universe had nothing, so where did all this matter come from? Although it may seem that everything came from something, scientists also consider the possibility that everything came from nothing, but what does nothing mean in science? To truly answer the question of how something could arise from nothing, we would first have to understand four interpretations of nothing. Our first interpretation of nothing is a state in which the essential components of everything we see were absent. Let us imagine a universe without galaxies, stars, planets, or even people. Everything that we know and interact with is composed of tiny subatomic particles. These particles are the basic components that form our universe. If we start from a universe full of matter, we can understand how it grows, cools, and is influenced by gravity to become the universe we see today. We know that stars go through life cycles, creating heavier elements that lead to the birth of new stars, planets, organic compounds, and, finally, life. But here are some big scientific questions. How did we end up with a universe dominated by matter, and not one with equal amounts of matter and antimatter? This is one of the biggest mysteries in physics. According to the laws of physics, matter and antimatter should be created in equal quantities, but our universe is composed almost entirely of matter, with hardly any antimatter at all. All the stars, planets, and galaxies that we have observed are composed of matter, so how did we arrive at this surplus of matter? This puzzle is known as baryogenesis, the creation process of an excess of baryons over antibaryons in the early universe. Scientists have many theories, but we still do not have a clear answer. We do not know why there is more matter than antimatter instead of a balance. To truly answer the question of how something could arise from nothing, we would need to understand four different forms of nothingness. Our second interpretation of nothing is the vacuum of vast space. Perhaps you think that nothing is really not having anything at all. If that is the case, then the first explanation of nothing with missing building blocks does not quite fit, because it still implies something's existence. To truly understand this concept of nothing, let us imagine that we get rid of all the basic elements of matter, which means eliminating each particle and every bit of energy. If we could eliminate all this, what would remain? Only the vast extension of empty space, without particles, matter, or any radiation. This is what some scientists consider the true scientific meaning of nothingness. But even in this extremely empty scenario, some fundamental aspects continue existing. The laws of physics remain in force, the quantum fields like the electromagnetic field, the gravitational field, the Higgs field, and the fields related to the nuclear forces continue existing. Space-time itself, guided by the principles of general relativity, continues existing. The speed of light and the gravitational constant continue conserving their values, and, what is more important, there exists something called zero-point energy. Even in the emptiest space there is still a small amount of energy that today we see as dark energy, that is driving the expansion of the universe. So even without matter or radiation, this version of nothing still gives rise to an intriguing universe. This takes us to the idea of a universe emerging from nothing. It is fascinating to think that, even in the absence of everything that we see, the universe can still be dynamic and captivating. The third interpretation of nothing for scientists is the idea of nothing as the lowest possible energy state for spacetime. At this moment, our universe has something called zero-point energy, which is a small amount of energy that exists everywhere in space. We do not know if this zero-point energy is the lowest possible energy or if there exists an even lower energy state that we have not yet discovered. There is the possibility that we are in a false vacuum state, with the true vacuum or the lowest energy state, either close to zero or perhaps even reaching or surpassing it. If the universe passed from this false vacuum to a true vacuum, it could trigger a catastrophic event called vacuum decay, that would drastically change the universe. Photons, which are particles of light, would acquire mass, the electromagnetic force would be confined to short distances, and most of the sunlight would not reach Earth. Thinking of nothing as the lowest energy state means imagining a situation in which all matter, energy, radiation, and any distortion in spacetime are eliminated, and what remains is a state of perfect vacuum, but the laws of physics would continue in force. In this state, there would still be a backdrop for events to occur, but without actors or actions. It would be like a play without characters, plot, or scenery, only an empty stage. This state of minimum energy would make it impossible to create any type of work, energy, or particles from it. However, some could still see this as something, since space, time, and the laws of physics would still exist. Now imagine reaching the true fundamental state of the universe, whatever it may be. In this state, all matter, energy, and any distortion in spacetime would disappear. What would remain is the definitive material vacuum. There would still be a stage for events to occur, but without actors or actions. It would be like a play without characters, plot, or scenery, only an empty stage. This state of definitive minimum energy would make it impossible to create any work, energy, or particles from it. However, some could still see this as something, because spacetime and the laws of physics would still exist. So our third interpretation of nothing is the lowest possible energy state for the universe. Even in this state, the framework of spacetime and the laws of physics remain. It is another incredible mystery that keeps scientists exploring and looking for answers. Our fourth interpretation of nothing is the most extreme. It is the idea that true nothing only occurs when the entire universe and its governing laws completely disappear. This is a radical idea that goes beyond our usual understanding of reality. Imagine getting rid of everything, including spacetime and even the laws of physics. This type of nothing is beyond what we can define with physics, because it represents an absolute vacuum, a total absence of everything from physics' point of view. This idea challenges how something like spacetime can exist if there is no space or time. How can the laws of physics function if there is no framework for them to exist? This type of nothing is difficult to understand and might not have any meaning in the real world. Thinking about this definitive nothing raises many questions without clear answers. For example, how could space and time begin in a place where they do not exist? Is it possible that there is something outside of the universe without space or something that begins without time? Imagine an absolute nothing, a complete void from physics' point of view. This idea is disconcerting, It suggests a state beyond the limits of space and time, from which our universe and its laws could arise. However, we are unsure if this idea makes sense or is just our imagination's product. This concept raises many difficult questions. For example, how can space and time begin in a place or moment where neither exists? Can we even imagine something existing outside the universe, without space or time? Where would the rules governing particles and their interactions come from? This idea of nothing, although philosophically complete, might not have any real substance. It could simply be a way of understanding things beyond our reality. When scientists talk about nothing, they often assume everyone has the same idea of what nothing means, but that is not always the case. Different people in different contexts can change our way of understanding nothing. The phrase, something from nothing, could mean creating something completely new where there was nothing before, but not everyone agrees on what nothing means. In the end, it's important to understand what version of nothing someone is talking about, because each has its own limits and applications. None of the tests, neither the cosmic background radiation nor the quantum fluctuation, suggests what was before the Big Bang. Even so, one of the most mysterious questions of cosmology is what there was before the Big Bang and what created that atom that later became the Big Bang. The Big Bang theory tells us that the universe began from an incredibly dense and hot point called a singularity. Think of a singularity as a point at which everything we know about space and time simply disintegrates. This singularity raises some important questions. If our usual laws of physics do not apply here, what are the rules for understanding this? Let's start with Albert Einstein's ideas. His theory of relativity changed our way of seeing the universe by linking mass and time. According to his theory, time is not fixed, but relative and changes depending on objects' gravitational fields. Objects with a significant mass. He showed that massive objects like Earth can slow down time. Now, if mass slows down time, imagine what the singularity does, which contains all the mass of the universe. It would stop time completely. So, according to Einstein, the idea of what was before the Big Bang does not make much sense, since time itself did not exist. The cosmic microwave background radiation is a key test, since it comes from a moment approximately 380,000 years after the Big Bang, when the universe was cooling and forming hydrogen atoms. Before 380,000 years, the universe went through several phases, starting with the Planck era, to the Great Unification, inflation, the electrostatic weak and the Ron eras of the Great Unification, inflation and electrochemistry. In each phase, different particles and forces evolved into what we know today. When we talk about the universe on such a small scale, quantum mechanics replaces classical physics, which led scientists like Stephen Hawking to think about how quantum theory could be applied to the entire universe. This is where inflationary quantum cosmology comes into play. Unlike classical theories that describe the singularity as a point with zero volume, cosmology suggests an element of uncertainty. This means that we cannot determine the exact moment when the universe was created and that particles can appear and disappear from what we call void. In physics, the void is not a state of absolute emptiness, but a state without particles. According to Heisenberg's uncertainty principle, there is always some level of fluctuation, so a perfect void with zero field values is impossible. This may sound strange, but Einstein's famous equation E equals mc squared helps explain it. The positive energy of the stars and galaxies must be balanced by an equal amount of negative energy, such as gravity. If the total energy of the universe is zero, then it is possible that it comes from nothing. The idea that hundreds of billions of galaxies can come from nothing sounds incredible, but Einstein's famous equation E equals mc squared gives us some clues. According to this equation, all the positive energy of the stars, galaxies and other celestial bodies must be balanced by an equal amount of negative energy, which appears as gravity in a closed universe or in one that will eventually collapse on itself. These positive and negative energies would perfectly cancel each other out, resulting in a net energy of zero for the universe in it. Stephen Hawking wondered how a universe with zero total energy could emerge from nothing. He suggested that the negative energy of gravity could balance the positive energy needed to create matter, which makes empty space stable. The physicist Alexander Villein took this idea further, demonstrating that a small void full of energy could spontaneously appear from nothing and expand to become the universe we see today. This means that our universe could have started from a state of nothing, where time did not exist. So, what was before the Big Bang? The theories we've explored suggest that time itself began with the Big Bang, which makes everything before a complicated concept, from singularities to quantum fluctuations. These ideas show how incredible and mysterious our universe is. The Big Bang theory explains how the universe expanded from a super hot and dense state, but it does not tell us what happened before that moment. According to the theory, time, space, matter, and energy began with the Big Bang. However, some scientists have ideas about what might have been before the Big Bang. An interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expansion and contraction, so the Big Bang that we know could have been just one of many bounces, with the universe constantly being reborn. Another fascinating idea is the concept of the multiverse. This theory proposes that our universe is only one of many universes, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another, completely different universe. These ideas exceed the limits of our current knowledge and delve into the realm of speculation. They are based on advanced concepts of quantum physics and the still theoretical field of quantum gravity. Scientists are trying to connect the dots between quantum mechanics and general relativity to better understand these possibilities. Although these theories offer exciting visions of what may have been before the Big Bang, they remain largely theoretical, highlighting the profound mystery of the origins of our universe. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question: where did this come from, and how was it formed? These questions continue until we reach a point where the only honest answer is that we don't know, at least not yet with what we understand. Then we are faced with intriguing questions: how did all this come about? After the Big Bang, the universe continued to expand and cool. At first, it was just a soup of tiny particles. As it cooled, these particles came together to form the first atoms, mainly hydrogen and helium. The life we see today is possible thanks to complex molecules that originally evolved from the simple atoms that appear in the periodic table. These atoms are the fundamental components of all ordinary matter in our universe. These atoms were not there from the beginning of the universe, but were formed through numerous cycles of birth, life, and death of stars. Each cycle of stellar life contributed to the nuclear reactions that produced these atoms, which were then recycled into new generations of stars. Without this continuous process, the creation of planets and the complex chemistry necessary for life would not have been possible. To understand how the stars and galaxies we see today came to be, a few key pieces must fit into place. First, gravity plays a huge role, attracting smaller groups of stars and galaxies to form the large galaxies we observe, kicking off new rounds of star formation. For gravity to do its job, there must be enough mass already clustered, and this is where dark matter comes into play. At the beginning, dark matter formed halos that helped prevent newly formed stars from scattering their material back into space. In addition to the right mix of matter, such as atoms, dark matter, and radiation, are crucial. This mixture not only produced the cosmic microwave background, a kind of afterglow of the Big Bang, but also created the light elements during that hot, dense state of the early universe. The growth of galaxies and star clusters depended on small initial differences in density, often called seed fluctuations, which needed to grow under the influence of gravity. Finally, there must be processes that initially created these density variations, dark matter, and the first batches of ordinary matter to capture ASP. To understand how our universe arose from the chaos of the Big Bang, we have to take into account some critical conditions from the beginning. On the one hand, the laws of physics, the structure of spacetime, and the essence of matter and energy were not there, they had to arise in some way: music. Let's delve into the mysteries of the universe. Matter, which makes up approximately 5% of the universe, includes the atoms and particles that form stars and galaxies. Dark matter, which represents approximately 27% of the universe, remains invisible and is only detectable through its gravitational effects on visible matter. Dark matter acts as a cosmic platform that guides the structure and formation of galaxies. The most dominant, but difficult to understand, component is dark energy, which makes up approximately 68% of the universe. This mysterious force drives the accelerated expansion of the universe, acting against the gravitational attraction of matter. Together, these components form the fabric of the cosmos, from the smallest particles to the largest galactic structures. We don't know exactly what dark matter and dark energy are, but we are quite sure that they are real. So, what is known? Dark matter is essential for galaxies to form. When scientists analyzed the structure of the universe, they realized that there is not enough regular matter. The gravitational force of visible matter is not strong enough to create galaxies or complex systems without dark matter. The stars would probably be randomly scattered instead of forming the magnificent galaxies we observe. This suggests that dark matter acts as a glue. This mysterious component that neither emits nor reflects light is known as dark matter. Although it is invisible, dark matter can be observed indirectly. Areas with high concentrations of dark matter deflect light that passes nearby, a phenomenon known as gravitational lensing. This deflection effect acts as a clue that reveals the presence of dark matter through its gravitational interactions. First, we know that dark matter is not simply ordinary matter without stars. Ordinary matter emits detectable particles that make it visible to our instruments. If dark matter were simply ordinary matter, we would have already observed it. Neither is it antimatter, since antimatter emits unique gamma rays when reacting with normal matter. If dark matter was antimatter, these gamma rays would provide a clear signal that we have not detected. Dark matter is not made of black holes, either. Black holes are compact objects that have a strong impact on their environment, while dark matter seems to be scattered throughout the cosmos. The gravitational effects of black holes differ from what we observe with dark matter. Scientists are exploring ideas and conducting experiments to discover dark matter's true nature. Even the precise 15-month study of the cosmos carried out by the Planck spacecraft of the European Space Agency was only able to detect less than 5% of the total observable universe. For years, scientists have tried to solve the dark matter mystery. They have only deduced its existence from the gravitational effect it seems to exert on visible matter. The renowned British physicist Brian Cox explains that dark matter could be some type of particle we still do not know. Dark energy is even more mysterious. We cannot detect it or measure it exactly, but we can see its effects. In 1929, the astronomer Edwin Hubble made a revolutionary discovery. He studied how the wavelengths of light coming from distant galaxies shift towards the red end of the spectrum as they travel through space. This phenomenon, known as redshift, revealed a surprising truth. Hubble discovered that the faintest, most distant galaxies showed greater redshift, while the closest exhibited it less. He concluded that this redshift was because the universe is expanding, since the wavelengths of light stretch and shift towards the red end of the spectrum, which indicates that space itself is growing. More recent findings have taken this discovery further. The universe's expansion not only continues but is accelerating. Previously, scientists believed that gravity would slow or even reverse this expansion. Scientists have discovered that this rapid rate of expansion results from dark energy, which is separating the universe at an ever-increasing rate. Space does not change its properties as it expands, but is constantly created everywhere. Galaxies remain tightly bound in clusters maintained by gravity, so we do not experience this expansion in our daily lives, but we see it everywhere in the universe. Wherever there is empty space, more is being formed every second. So what is dark energy? It seems to be some kind of energy in empty space, stronger than anything else we know, and that is constantly increasing. Empty space contains more energy than everything else combined in the universe. This mysterious force is separating the galaxies, accelerating the universe's expansion. Dark energy remains one of cosmology's greatest mysteries. Although we cannot detect or measure it directly, its influence on the universe is undeniable. As we continue to explore and study the cosmos, we hope to unravel this enigmatic force's secrets and get closer to understanding the true nature of our ever-expanding universe. The discovery that this expansion is accelerating suggests that dark energy, a mysterious force, is acting. Understanding dark energy is one of the greatest challenges of current cosmology, but how do we find dark matter? Scientists are looking for this mysterious dark matter using the world's largest physics experiment at CERN in Switzerland, the Large Hadron Collider. Instead of trying to find it, they are trying to create it from scratch. They do this by colliding known particles at very high speeds to create enormous energy in these impacts. This energy could produce dark matter particles. When protons collide, they usually create new particles, but these are usually low-mass particles. However, very rarely, these collisions produce much heavier particles, and those are the ones scientists are looking for. So, the search for dark matter continues in CERN's underground laboratories, and by observing the night sky, scientists believe they are getting closer to discovering what it is made of. The most popular candidates for dark matter are called weakly interacting massive particles. It is hypothesized that these particles interact very weakly with normal matter, making them incredibly difficult to detect. Underground detectors aim to observe these infrequent interactions and provide clues about dark matter's nature. One of the most fascinating tests comes from gravitational lensing, a phenomenon that occurs when light from distant objects, such as galaxies or quasars, curves around a massive object, like a cluster of galaxies, due to gravity. The amount of curvature observed can reveal the presence of dark matter, as it contributes to the total gravity. Astronomers also play a key role in the search for dark matter by observing the night sky. They study the behavior of galaxies and clusters of galaxies. The way these massive structures move and interact provides indirect evidence for the existence of dark matter. For example, the rotation curves of galaxies and the speed at which stars orbit around the center. The gravitational effects we observe suggest that much more mass is present, and that is attributed to dark matter. Although we have not yet directly detected dark matter, each experiment brings us closer to understanding this mysterious component of the universe. In 1950, Enrico Fermi, a famous physicist, asked a simple but important question during a lunch discussion with his friends about extraterrestrial life. He wondered why, given the galaxy's immensity, we have not found any sign of advanced civilizations. Before continuing, let's understand why the Fermi paradox is called a paradox. Let's imagine how many stars and planets exist in our galaxy. It is estimated that there are approximately 400 billion stars. If only a small fraction of these planets harbored intelligent life, these civilizations would have had plenty of time to spread throughout the galaxy and colonize many planets, possibly including Earth. However, we see no evidence of it or alien visits that explain why we have not found any extraterrestrial civilization, despite the high probability of its existence. Several theories have been proposed. Travel between solar systems could be incredibly expensive and require many resources. For example, sending a spacecraft to the nearest star could cost an enormous amount of money and energy, which would make it impractical. Even if a civilization began to colonize other planets, it would be a great challenge to continue expanding continuously, since not only would the first trip be needed, but the settlers would have to survive and continue expanding from one star to another, generation after generation. Perhaps the galaxy is full of activity in other parts, but we are in a quiet area where little happens. Another idea is that Earth is like a zoo or a nature reserve where aliens watch us from a distance, ensuring we don't bother each other and we don't realize their presence. To understand the historical background of the Fermi paradox, we must consider two key ideas. The first is the Drake equation, created by Frank Drake, a prominent figure in the search for extraterrestrial intelligence. This equation suggests that there could be thousands of alien civilizations capable of sending signals to us. The second idea is Fermi's own paradox, which questions why we have not seen clear signs of intelligent extraterrestrials, such as evidence of interstellar colonization. The term Fermi paradox is somewhat misleading, since it was erroneously named after the physicist Enrico Fermi, who never proposed such a theory. Despite this, the concept is important in debates about extraterrestrial life and has influenced funding for related research. It has even affected political decisions, such as Senator Williams' pressure to end NASA's SETI program in 1981. Although the program was briefly reactivated after Carl Sagan advocated for it, it was closed again in 1993 by Senator Richard Bryan. However, the search for extraterrestrial intelligence has not ended. Although NASA no longer funds SETI projects directly under the same initiative, the search continues through other means and with other funding sources. Projects such as the SETI Institute, which is a private non-profit organization, continue the work. The SETI Institute collaborates with academic institutions, private companies, and government entities, including NASA, to continue its research. The term Fermi paradox was not first proposed by Enrico Fermi. We only know what he thought about it through the work of physicist Eric Jones, who collected the memories of 3 of Fermi's colleagues who were with him at a lunch in Los Alamos in 1950. These colleagues, Emil Konopinski, Edward Teller, and Herbert York, recalled Fermi's question about space travel. It was from this conversation that the idea now known as the Fermi paradox emerged. According to Herbert York and Edward Teller, Fermi was more curious about whether it was possible to travel between stars than whether extraterrestrials existed. The term Fermi paradox suggests the lack of conclusive evidence of extraterrestrial life, but this is not what Fermi himself believed. His doubts were about the possibility of space travel, which made sense at that time, back in 1950. Rockets couldn't even reach orbit, let alone another planet or a star. The idea that there were no extraterrestrials on Earth meant that there were no extraterrestrials anywhere was first published by astronomer Michael Hart in 1975, not by Fermi. Michael Hart argued that if intelligent extraterrestrials existed, they would probably have already colonized the Milky Way, from which he concluded that their absence on Earth suggests that humans may be the only intelligent beings in our galaxy. He believed that searching for extraterrestrial intelligence could be a waste of resources. However, this perspective has been criticized for several reasons. Critics point out that interstellar travel could be impossible, that civilizations could choose not to colonize other planets, or that extraterrestrials could have visited Earth a long time ago, in prehistoric times, without leaving any obvious traces. Despite the criticisms, Michael Hart's hypothesis remains an important topic in debates about extraterrestrial life. In 1980, physicist Frank Tipler built on Michael Hart's ideas to address a major challenge: the enormous resources needed to colonize billions of stars. Tipler proposed the idea of self-replicating robots with human-like intelligence. These machines could be sent to a nearby star, use the resources available there to make copies of themselves, and then those copies could spread even further, potentially filling the entire galaxy. Frank Tipler concluded that, since we have not found such advanced self-replicating machines on Earth, this suggests that we may be the only intelligent civilization not only in the Milky Way, but in the entire universe. This is a bold conclusion that is drawn from not having found extraterrestrial beings. The idea, commonly known as the Fermi paradox, actually comes from the theories of Hart and Tipler. Over time, their ideas have been mistakenly confused with Fermi's initial question, leading to some confusion about the origin and intent of the paradox. This confusion seems to have started in 1977, when physicist David Stevenson used the term Fermi paradox in a publication in which he presented Hart's theory as an answer to Fermi's question. A more accurate name for this reasoning might be the Hart-Tipler argument against the existence of technological extraterrestrials. This title, although not as catchy as the erroneously attributed Fermi paradox, would more correctly honor the true creators of the idea. The search for extraterrestrial life remains an important goal for scientists. The James Webb Space Telescope is providing us with incredible new images and data, and the Mars rovers are investigating the planet up close. There are also plans for future missions to explore the confines of our solar system. The question of whether we are alone in the universe remains open and, until we find an answer, the search for extraterrestrial life will remain a priority for humanity. Scientists have found several ways to look for life beyond Earth. A key area of research is the study of exoplanets, which are planets that orbit stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, some of which are in the habitable zone, where conditions could be suitable for life. The habitable zone is the region around a star where temperatures could allow the existence of liquid water. Liquid water is essential for life as we know it, making these exoplanets prime candidates for further study. For life to exist, certain ingredients are needed in addition to liquid water. Life requires essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements form the basic components of organic molecules, which are the basis of all known forms of life. Interestingly, these elements are abundant in the universe. They have been detected in interstellar clouds, comets, and even on the surfaces of other planets and moons in our solar system. Scientists are also looking for biosignatures, which are signs of life that can be detected remotely. Biosignatures may include specific gases in the atmosphere of a planet, such as oxygen or methane, which could indicate the presence of biological processes. Another area of intriguing research is the search for technological signatures, which are evidence of advanced civilizations. This includes searching for radio signals, laser pulses, or other technology forms that could indicate intelligent life. Projects such as the search for extraterrestrial intelligence have scanned the skies for decades, hoping to detect a signal from an alien civilization. While focusing on life beyond Earth, scientists are also investigating the possibility of life within our solar system. Moons like Europa and Enceladus, which have underground oceans beneath their ice layers, are particularly intriguing. Protected by a thick layer of ice, these oceans could provide the necessary conditions for life, away from the hostile environment of space. As technology advances, our ability to search for extraterrestrial life will continue improving. New telescopes, space missions will improve our ability to detect and analyze possible signs of music. On the night of July 15, 1977, Jerry, a volunteer in the search for extraterrestrial life, monitored radio signals when he found a strong, unusual signal. This signal, which lasted 72 seconds, was 30 times stronger than typical background noise and came from the direction of the Sagittarius constellation. The computer converted the received signals into a series of alphanumeric characters that resulted in the sequence 6x5. The signal was so shocking that when the technician reviewed the print the next morning, he wrote "Wow" on it. This reaction gave the signal its name, the "Wow" signal, and it has fascinated the international scientific community ever since. It was concluded that the source of the signal emitted in a regular pattern similar to the sweeping beam of a lighthouse, so it seemed as if we captured the signal when it was directly in front of us, and then lost it as it moved away, spinning. Even after extracting and monitoring the signal, the "Wow" signal remains one of the most compelling pieces of evidence, and its origin remains the subject of much speculation and study as to whether or not it was a message from extraterrestrials. It remains a mystery. Scientists even believe that the "Wow" signal detected was not complete, but that the signal could have been transmitting in a regular pattern. To truly answer why we didn't hear the full signal, we need to know the telescope's behavior. The "Wow" signal was detected using the Big Ear telescope of the Ohio State University, which was specifically designed as part of its search for extraterrestrial intelligence. The telescope, approximately the size of 3 football fields, had a large mirror at one end that captured signals and reflected them onto smaller mirrors at the other end, toward 2 receivers in the center for processing. However, the Big Ear telescope's design made it difficult to constantly detect the signal. After the telescope captured the "Wow" signal, there was a delay of a few minutes before its second receiver could check the same area of space from which the signal originated. By the time the telescope was ready to look again, the signal disappeared. This absence of regular detection poses a significant challenge to confirming the signal's origin. The Big Ear telescope structure and operation highlight a possible confirmation bias problem. If the telescope could continuously monitor the signals or quickly return to the same region of space, researchers could have confirmed whether other similar signals came from the Sagittarius constellation. This would provide clearer proof of its origin. This limitation shows the importance of telescope design in the search for extraterrestrial signals. The Big Ear telescope was a radio telescope, so it did not use traditional mirrors like optical telescopes, but rather wire-capture parabolic antennas to detect radio frequencies, wavelengths invisible to the naked eye. Unlike modern telescopes, which can rotate freely to explore different parts of the sky, Big Ear could only tilt its main reflector up and down, limiting it to observing a narrow strip of sky at a time. This design was chosen because it was more cost-effective and simpler to build compared to more complex systems. However, Big Ear's designers devised an ingenious solution to expand its observation range by using the Earth's rotation to move the telescope left and right and adjusting the tiltable reflector to cover different vertical angles. Over time, Big Ear could observe any point in the sky. This use of the natural rotation of the Earth was an innovative solution to the design limitations of the telescope, allowing it to maximize its observation potential despite its limited mobility. This strategic use of natural and mechanical adjustments made Big Ear a unique and valuable tool in the search for extraterrestrial signals. The design of the Big Ear telescope presents significant observation limitations due to its movement with the Earth's rotation, as it could not continuously monitor the same point in the sky for long periods of time, which means that it could have missed additional signals from the same region. Imagine an entire orchestra of complex signals being transmitted from that point in the hours after the "wow" signal. Big Ear, due to its design, may have captured only a fleeting glimpse of a single note of what could have been an extraterrestrial communication symphony. This limitation reflects a broader strategy used by organizations such as SETI in the search for intelligent life in the universe. Given the immensity of space and limited resources, these organizations must make strategic decisions about how to use their equipment. They cannot afford to dedicate a telescope to monitoring a single area of space for years, hoping to get an answer. Instead, they use a more dynamic approach, sweeping wide areas of the sky with their telescopes to cover as much territory as possible. This method is like casting a wide net at various points instead of waiting indefinitely in one place. By continuously moving and scanning different areas, they maximize their chances of detecting signals, even briefly, which is more practical, given the uncertainties involved in finding where and when a signal from an intelligent extraterrestrial source might appear. The analogy of SETI's search efforts with fishing could oversimplify the complex task of searching for extraterrestrial intelligence, as alien signals are not like fish that are caught. Unlike fish, which can be attracted or repelled by certain actions, alien signals are not influenced by our attempts to detect them. Sweeping the sky with a telescope may seem random, but it is a practical method, given the immensity of space and the unpredictability of where and when a signal may appear. However, this method presents challenges, especially in tracking them over the years. Radio telescopes like Big Ear have detected several unusual and fleeting signals similar to the WOW signal, strange bursts of radio waves for which we currently have no explanation. The problem is that, without sustained observation and focused study of these signals, they remain mysterious and underinvestigated. This lack of exhaustive follow-up means we potentially miss valuable data that could lead to solid findings about its origin. This leads to an important conclusion: the possibility that we have not detected intelligent extraterrestrial life could be significantly influenced by our observation methods. Of course, this is just one of many possible explanations. In this debate we have addressed some of the technical challenges posed by the detection of signals of extraterrestrial life. There are also numerous more speculative explanations based on theories about our place in the universe and the nature of other civilizations. These theories provide compelling ideas and open intriguing possibilities about our understanding of life beyond Earth. If you found this topic interesting, stay tuned, as I plan to explore these more speculative theories in another video that will offer a deeper insight into extraterrestrial life beyond Earth. The question of whether aliens are watching us from the night sky is as fascinating as it is complex. The large number of stars and galaxies in the universe suggests that conditions for life, even intelligent life, could exist beyond Earth. If only a small fraction of the planets around these stars could harbor life, that would imply that life could be relatively common in the cosmos. The reasons why we have not yet established contact with extraterrestrial civilizations could be numerous. One possibility is the immense distance separating the stars, which makes communication and travel through space a significant challenge. In addition, the timing might not coincide. Civilizations could arise and disappear asynchronously with each other, missing opportunities for contact. Another intriguing aspect is the nature of communication itself. Advanced civilizations could use technologies or communication methods that are beyond our understanding or detection capacity. It is also possible that advanced civilizations intentionally avoid making contact with species like ours, observing us as we study species less advanced than us. The WOW signal, an inexplicable anomaly detected in 1977, highlights both the potential and challenges of the search for extraterrestrial intelligence. Despite extensive efforts to detect it again, the nature of the signal continues to provoke curiosity and speculation. It serves as a compelling reminder of how much we still have to learn about the universe and our place in it. Ultimately, the search for extraterrestrial life is driven by our innate curiosity and a deep desire to answer one of humanity's oldest questions: are we alone in the universe? Regardless of whether we make contact in our lives, the search for this knowledge continues to expand the limits of human understanding and exploration. The day we make first contact, if it ever comes, will undoubtedly be a defining moment in human history. What will happen after that? What will it mean if we receive and confirm a signal from aliens? How would this affect our lives, our priorities, our vision of the world, and our own identity? Will we be prepared for such a discovery? The main goal of SETI is to find a clear and repeatable signal from outer space similar to the famous WOW signal, to confirm that we are not alone in the universe. We would need to capture those signals more than once to be able to contact aliens. We would have to send them a message and get a response, or they would have to send us a message first. We could try to contact by sending spaceships or robotic probes, but traveling through space with our current technology is very slow. For example, the Voyager 2 probe took about 49 years just to leave our solar system to reach the nearest star system, which is 4 light-years away. At the speeds we can currently reach, it would take us more than 81,000 years, which is equivalent to 2,700 generations of human beings, so unless the closest aliens are right next door, in the nearest star, reaching them would be incredibly difficult. Even if we were better at building spaceships, reaching the speed of light is almost impossible, as it would require more energy than we can gather, basically more than is available in the entire universe. That means we can't travel as fast as light, which limits how far we can go. However, there could still be hope. Some scientists are exploring ideas such as creating wormholes that can move space itself, which, in theory, would allow us to travel faster than light without breaking the known laws of physics, because the rule about speed limits only applies to movement through space, not to the movement of space itself. For now, sending messages through space as radio signals is much easier and cheaper than sending ships. It's like calling someone on the phone instead of visiting them. It saves time and effort. Most likely, if we ever come into contact with aliens, it will be because we received one of their calls, even with the speed of light, which is incredibly fast, about 300 million meters per second, is still the maximum speed at which any signal can travel, such as light or radio waves. This speed sets a limit on how quickly we can communicate over long distances in space. So that we can communicate with aliens, any message we send has to travel through space to reach them and, if the aliens respond immediately, their message has to travel all that way back to us. This means there is a large delay in communication. We only started using radio technology in the mid-1890s, so we haven't been able to do this for very long. As such, we could only exchange a message with aliens living a maximum of 60 light-years from us. 60 years for a signal sent in 1900 to reach the alien civilization and 60 years for it to return. Music. Humanity has been sending radio signals into space for about a century. These signals have spread approximately 100 light-years from Earth, which could alert extraterrestrial civilizations within this range. Beyond this bubble, Earth's presence is almost undetectable. As technology advances, our unintentional radio emissions are decreasing, which could lead to a future of radio silence. The short lifespan of a civilization's radio signals in the grand scheme of cosmic time poses a significant challenge for interstellar communication. In addition, these signals weaken as they travel through space. Why haven't we found any signals from alien civilizations in such a vast universe, full of countless stars and planets? This disconcerting situation, known as the Great Silence, suggests a universe empty of detectable signals or indications of aliens, which challenges our understanding of the apparently infinite cosmos. In 1967, Jocelyn Bell, a student at Cambridge University, was conducting studies of the sky with a new radio telescope. Its constant synchronization did not resemble anything previously observed, which led to speculation about extraterrestrial origins. The source was baptized with the humorous name of LGM-1, abbreviation of Little Green Men, which reflected the initial enthusiasm for a possible extraterrestrial communication. However, the mystery was soon resolved as a natural phenomenon. The signal came from a pulsar, a type of neutron star that rotates rapidly and emits beams of radiation very similar to those of a lighthouse. Despite intense efforts in the search for extraterrestrial intelligence, no definitive extraterrestrial signals have been detected. Military radar signals, among the most powerful emissions, are more likely to be detected at great distances than standard television broadcasts. The Next Square Kilometre Interferometer, a large interferometer located in South Africa and Australia, could be able to detect weak signals from civilizations similar to Earth several hundred light-years away. Deliberate attempts at communication, such as the Arecibo message of 1974 sent from Puerto Rico towards a distant star cluster, offer a more focused approach. However, these efforts are brief, giving extraterrestrial observers a small window to detect them. An example of a possible extraterrestrial signal is the WOW signal of 1977, a brief burst of energy that was never conclusively explained or detected again. Ultimately, the chances of two civilizations meeting through random transmissions are very low. To improve our chances of making contact, we must search more strategically, focusing on signs of technological and biological life in the universe. In 1995, astronomers made a revolutionary discovery: the first planet orbiting a star similar to our Sun outside our solar system. Since then, we have discovered that most stars in our galaxy probably have at least one planet, with billions similar to Earth in size and orbiting in the habitable zones of their stars. This zone allows for the possibility of liquid water, a crucial component for life as we know it. Even moons orbiting these planets could harbor life, with estimates suggesting that there could be up to 1 billion such moons. Recognizing this potential for extraterrestrial life, in 2017 scientists sent a message directed to one of the most Earth-like exoplanets we have discovered, which is relatively close to us. This message included musical pieces and information about humanity. If the planet is inhabited and able to respond, we could receive a response by 2044. Determining if a planet has life involves detailed examinations, such as analyzing the chemical composition of an exoplanet's atmosphere by observing starlight passing through it. For example, an oxygen-rich atmosphere similar to that of Earth could suggest the presence of life, since on our planet oxygen is largely produced by photosynthetic organisms. However, the presence of oxygen alone is not conclusive, as it can also be produced by non-biological processes. Astrobiologists are particularly interested in specific chemical combinations unlikely to coexist without life, such as methane and oxygen. In addition, certain chemical compounds such as carbon dioxide could indicate industrial activity and climate change, serving as indications of intelligent life. By studying these chemical markers, scientists hope to find evidence pointing to the existence of life beyond Earth. Beyond biosignatures, we could also detect technology-related indicators known as technosignatures. For example, an exoplanet with a dense belt of artificial satellites or space debris could be identified when it transits its star. Another example is the theoretical construction known as a Dyson sphere, proposed by physicist Freeman Dyson. These hypothetical megastructures could be built by advanced civilizations to capture the energy of a star. The Kardashev scale, introduced by astrophysicist Nikolai Kardashev, classifies civilizations based on their energy consumption. A Type 1 civilization uses the energy of its planet, a Type 2 civilization harnesses the energy of its star, and a Type 3 civilization uses the energy of an entire galaxy. Although there is no confirmed evidence of Type 2 or Type 3 civilizations in the Milky Way, these concepts inspire and guide our search for extraterrestrial intelligence. Given the large number of Earth-like alien worlds, many believe that life on our planet is not unique. In fact, it is estimated that there are more than 300 million planets with Earth-like conditions within our galaxy, the Milky Way. This leads us to a big question: are we alone in the galaxy? Given our discovery of more than 4,000 exoplanets orbiting other stars, we have learned that almost every star has at least one planet, and approximately one-fifth of these stars have Earth-sized planets orbiting them. With around 100,000 million stars in the Milky Way, we are talking about billions of potential Earth-sized planets. Thinking that we are the only ones with life seems unlikely, given the odds. The Hubble Space Telescope can observe around 100 billion galaxies. If we take into account that each of these galaxies contains around 100 billion stars, the total number of stars in the visible universe is approximately 10 trillion. This number is almost unimaginable for human understanding. Given its immensity, it seems likely that there is life in the universe. Let us consider the immensity of our universe, filled with a mind-boggling number of stars. Our own Milky Way, according to the most conservative estimates, is home to between 100,000 and 400,000 million stars, but the Milky Way is only one among countless galaxies spread throughout the universe, so even if the chances of intelligent life developing are incredibly small, the overwhelming number of stars still hints at the possibility that we are not alone. The numbers suggest a universe where the formation of life somewhere seems almost inevitable. Frank Drake was a key figure who tried to solve the mystery of how many detectable civilizations might exist in our galaxy. He outlined a series of questions that scientists needed to answer to arrive at this number. By combining these questions and multiplying the answers, he created what we know today as the Drake equation. This formula gives us an estimate of the number of detectable civilizations in our galaxy. For more than 6 decades, the Drake equation was our main tool for estimating the number of civilizations in the Milky Way, suggesting that there could be between 1,000 and 100 million planets harboring civilizations in the Drake equation. Our asterisk represents the rate at which new stars are formed in our galaxy each year. Next, FP measures the percentage of these stars that have planets orbiting them. Then we consider which of these planets are within the habitable zone, where conditions could support life. This part of the equation is called Kn and is a number that is still largely unknown because we don't know much about the planets outside of our solar system. These planets could harbor life, but how many actually do so? That is what FL tries to find in the Drake equation. Finally, Phi estimates how many of these habitable planets actually develop intelligent life. Frank Drake focused on radio astronomy when he created the equation. His goal was to find out the possibilities that extraterrestrial civilizations could be sending detectable signals with our current technology, a concept included in his equation as Fc. In the 1960s, many scientists believed radio waves were the most likely method an advanced alien civilization would use to communicate. Earth itself has been sending radio signals into space for almost a century, reaching stars within 80 light-years. However, this raises a persistent question. Do intelligent life forms elsewhere in the universe still use radio waves, or might they consider that technology as outdated as we consider smoke signals? The last variable in the Drake equation, represented by L, tries to determine how long a technological civilization can be detected across the cosmos. Drake was concerned that, while a sophisticated society might briefly emit detectable signals, this period might be just a flash in its long history, so even if civilizations lasted millennia, we might only glimpse them. When Drake made his first calculations in 1961, he estimated that there were between 4 and 10 detectable civilizations in our galaxy. However, using current scientific knowledge to update Drake's parameters, one arrives at a very different number. The new estimate of n, the number of detectable civilizations, is only 0.127. This means that, in every 100,000 years of our galaxy's history, approximately 127 civilizations could become detectable. Drake's belief in a Milky Way dotted with some 10,000 civilizations shapes a vision of a vibrant cosmic community, but the reality of finding a single one among at least 100 billion stars highlights the enormous magnitude of this challenge. This suggests that astronomers would have to study 10 million stars before they could claim these civilizations are rare, underscoring the monumental task at hand. We still don't know how many alien civilizations might exist out there. Estimates range from a few to up to 100 million civilizations in the Milky Way, but some think we might be the only advanced civilization in our galaxy. That doesn't mean we're alone in the entire universe, which is incredibly vast. The observable universe extends about 92 billion light-years and contains between 100 billion and a trillion galaxies, each with about 100 billion stars, which means there could be up to 10 to the power of 23 stars and probably as many Earth-like planets, so it is likely that other intelligent life exists somewhere, but perhaps not in our Milky Way. Throughout Earth's history there have been more than 10 billion species, but none have shown the intelligence, curiosity, and ability to build complex tools like humans. Even intelligent animals such as whales and dolphins do not appear to think deeply or make complex tools. Human beings appeared only a few 100,000 years ago, so for most of Earth's history, an alien looking at our planet would not see any advanced technology or signs of superior intelligence. Furthermore, it is not clear if being so intelligent is beneficial for us in the long term. Our intelligence has helped improve the lives of many people in recent centuries, but it has also brought us closer to self-destruction. Astronomers have been trying to get better estimates of how many alien civilizations there might be in our galaxy. They focus on two major unknowns: the probability that life begins on Earth-like planets from non-living materials and the chance that this life becomes intelligent. Even with these estimates, there is much disagreement about what this means for life elsewhere in the universe. Some scientists point to the large number of Earth-like planets and argue that we cannot be alone. Others, however, want solid evidence and wonder that if there are so many civilizations out there, why haven't we found any sign of them yet? This question is at the heart of what is known as the Fermi paradox: if extraterrestrial life is common, where are all the aliens? Although the search for extraterrestrial intelligence has been actively scanning the sky, we have only looked a few hundred light-years away, which is only a small part of our galaxy. If our galaxy were full of life, especially advanced life, some of it would be much more developed than us. Long ago, the stars in our galaxy went through processes that created the elements needed for Earth-like planets to exist. There could be civilizations out there that were billions of years more advanced than us. Considering how fast it has progressed in recent centuries, imagine what a civilization could do in thousands or even millions of years. If such civilizations existed, they could travel between stars and colonize the galaxy. In theory, they could populate the entire galaxy in just a few million years, so if such advanced beings existed, we might expect them to have already contacted us. It's truly amazing to think that we live in one of the few places in the universe where life is possible. We are not overwhelmed by extreme conditions such as scorching heat, freezing cold, or dehydration. It almost seems like we are incredibly lucky. Our unique position on Earth, perfectly situated in its life-supporting environment, gives us a special perspective on the universe. This point of view could even help us understand the Fermi paradox, the question of why, given the immensity of the universe, we have not found other forms of intelligent life. Here is an interesting point to consider: our Sun is stable, which is unusual. Long ago, an object the size of an airplane collided with Earth, and the remains became our Moon. This event made Earth's core larger than usual for a planet of its size. We are in the Goldilocks zone, where it is neither too hot nor too cold for life. Our large corona is a strong magnetic field that protects us from harmful solar radiation. Our solar system is unusual because, in most systems, the largest planets are closer to the star than the smaller ones. Nature often favors strength over intelligence. If not for the asteroid that helped exterminate the dinosaurs, we humans would not have become the dominant species. That asteroid was big enough to wipe out the dinosaurs, but not so big as to wipe out all of life. A stroke of luck for us. We also have a balance between land and water, which helps create a climate system that sustains life. Our Moon has the right size and distance to create tides and seasons. Without it, our oceans would be stagnant, and we would have constant earthquakes and volcanic eruptions that would make life difficult. Jupiter, our giant neighbor, acts as a shield that blocks most of the asteroids that could collide with Earth. We are also not near the center of the galaxy, which is full of dangerous gamma rays, pulsar radiation, supernovas, and black holes. Earth has been unusually peaceful in terms of natural disasters, more so than usual in Earth's history. We have been lucky to avoid massive volcanic eruptions, large earthquakes, and ice ages recently. With all these factors, think about how rare it is that the other 20 billion potentially habitable planets have all these same qualities, and even if there is one with all these characteristics, what are the odds that it has, and if it has, how many of those civilizations have survived plagues, natural disasters, cosmic events such as asteroids and solar eruptions, famines, ice ages, and even wars between them, taking into account all the planets capable of sustaining life? Finding another planet with life is like crossing the Sahara Desert and finding a single gold bar. It could even be more likely that any alien we find is actually a human from a distant future. Despite its soft name, the rare Earth hypothesis is a very important concept. It basically says that we have to be in a part of the universe that can harbor life like Earth, instead of in the vast, empty spaces between galaxies. This may seem like common sense, but recognizing this bias in our observations is key to understanding why the universe looks the way it does from our location. The weak anthropic principle, combined with the fact that we have not found other civilizations, could mean that intelligent life is very rare in the universe. Think about the nature of being an intelligent observer like you. The mere fact that you are thinking about these concepts is a unique experience that is happening now. This type of awareness, your specific awareness, could be extremely rare, perhaps even unique, and can only exist under very specific conditions. However, here you are living this conscious experience. However rare the environments that allow life may be, you inevitably find yourself in one. The weak anthropic principle does not say that these environments are common. For example, if there is only one planet with life in the galaxy or even in the entire universe, it would have to be the one you are on. The rare Earth hypothesis suggests that Earth is exceptionally unique and perfectly suited to harbor intelligent life due to specific factors. This idea is supported not only by the distinctive characteristics of Earth but also by the remarkable absence of extraterrestrial life, which is emphasized in the Fermi paradox. This paradox highlights the contradiction between the enormous potential for life throughout the galaxy and the actual lack of evidence of other civilizations. We have already talked about the Fermi paradox and its explanations, but let's think about the possibility that it shows us a simple truth: technological civilizations are extremely rare, perhaps because planets like Earth are extraordinarily uncommon. The Fermi paradox also leads us to the concept of the Great Filter, which suggests that there are difficult or improbable stages in the evolution from a lifeless planet to a civilization that can be detected through technology. One of those filters could be imminent threats such as climate change or nuclear war, which could still pose a risk to our survival. However, the rare Earth hypothesis presents a more hopeful scenario by proposing that planets capable of harboring civilizations like ours are very rare. This theory was popularized by Peter Ward and Donald Brownlee in their 2000 book, which focuses on the specific traits of Earth that are necessary for life and intelligence to develop, while Earth-like planets that are rocky, similar in size to Earth, and located in the habitable zones around their stars, appear to be quite common. It is important to understand what makes Earth unique in harboring life. The Kepler mission suggested that there could be around 10 billion such planets in our galaxy alone and that this number could rise to 40 billion if we include planets orbiting stars other than our Sun. This abundance suggests that, statistically, if just one civilization had a slight technological or evolutionary advantage, it could have spread throughout the Milky Way by now. However, the fact that we have not observed any such interstellar colonization suggests that truly Earth-like planets, with all the conditions necessary for complex life, could be much rarer than the simple criteria of size, composition, and orbit suggest. To understand the unique qualities of Earth, we can start by identifying the characteristics crucial for life as we know it. If a specific characteristic of Earth that sustains life is also found on another planet, it could indicate that such characteristics are common. Conversely, if certain characteristics of Earth are unique in our observations, these could be incredibly rare. The weak anthropic principle reminds us that it is not a coincidence that we find ourselves on a planet that has these rare characteristics that sustain life, given our current knowledge and technology. Our comparisons are limited to the rocky planets in our own solar system, which provides context but also shows how little we know about the large number of exoplanets. Two key characteristics make Earth unique: its dynamic interior and its large moon. First, Earth's core is composed of a solid iron inner core surrounded by a molten metal outer core. The movement within this outer core generates a strong magnetic field that acts as a shield against harmful space radiation and solar storms. Above the core, the mantle is solid but flows slowly, driving the movement of tectonic plates. The Earth's crust is divided into these plates that float on the mantle and occasionally sink into it through a process called subduction. This tectonic activity is crucial, as it leads to significant environmental changes that promote biodiversity by altering ecosystems. It also recycles nutrients with materials from the crust that move into the mantle and then back to the surface through volcanic activity, which is essential to maintaining a rich biosphere. Secondly, Earth's large moon plays a fundamental role in stabilizing our planet's climate by moderating its tilt, which helps maintain a relatively stable climate that favors life over long periods. The moon also contributes to the tides, which have been important in the development of life in Earth's early history. In contrast, Mars does not show any significant tectonic activity, and Venus, if it has any tectonic movement, shows it on a much more limited scale. Neither Mars nor Venus have a protective magnetic field like Earth's. While it is difficult to know how common tectonic activity is on exoplanets due to our current technological and knowledge limitations, the combination of Earth's dynamic geological activity and a large, stabilizing moon could be uncommon, distinguishing our planet as unique and suitable for life. The Earth's moon is unusually large in comparison to the moons of other rocky planets in our solar system, a characteristic that could be extremely rare on a cosmic scale. Its significant size, composition and orbit suggest that it was formed from the remains of a massive collision between the Earth and a planet the size of Mars in the beginnings of the history of our planet. This catastrophic event probably played a crucial role in configuring the conditions favorable to life on Earth. It is believed that the collision accelerated the rotation of the Earth, which gave rise to shorter nights, important for the photosynthesis processes on which many forms of life depend. It also established the axial tilt of the Earth, which is moderate enough so that we have seasons that are not too harsh. Our planet's inclination is in what could be considered a zone of climatic stability, which may be uncommon among planets. In addition, the impact is believed to have initiated tectonic activity by fracturing Earth's primitive crust. The gravitational attraction of the Moon also contributes to the tectonic dynamics of the Earth by exerting tidal forces that can stimulate geological activity. These factors have had profound implications for the environment of the Earth, making it a propitious home for life. Such a combination of moon-induced effects could be quite uncommon in the galaxy, adding another layer to our planet's uniqueness. Another interesting theory is that the Moon may have influenced the origin of life on Earth. It suggests that life could have begun in tidal pools where the Moon's gravitational attraction created the right conditions for complex chemical compounds and the first known life forms, known as protocells, to develop. In addition, our entire solar system is quite distinctive compared to others we know. Knowledge from the Kepler mission has shown that the diversity of planet types in our system is unusual. We have everything from small rocky planets like Mercury to large gas giants like Jupiter and Saturn. In most other systems, planets tend to be more uniform in size, and large planets like Jupiter and Saturn are rare, appearing in only about 10% of the observed systems. Jupiter, in particular, could have been vital for life on Earth. Its strong gravitational attraction acts as a cosmic shield that captures or deflects many comets and asteroids that might otherwise have collided with Earth. By avoiding these possible mass extinction events, Jupiter may have allowed life on Earth to evolve without major disturbances. This role of Jupiter and the diverse composition of our solar system contribute to the unique conditions that sustain life on our planet. Other factors could contribute to the uniqueness of Earth, such as its favorable atmosphere and the abundance of water, also the fortunate avoidance of cosmic disasters like gamma-ray bursts. However, what could really differentiate Earth is the unique trajectory of its evolutionary history. While simple life forms may be common throughout the universe, the leap from single-celled life to complex life and then to intelligent life could involve extremely rare evolutionary steps. A significant example is the formation of the eukaryotic cell. This appears to have been an uncommon evolutionary event in which two types of simpler cells merged, with one becoming the mitochondria within the other. This fusion greatly increased the complexity of the cell, paving the way for the development of multicellular life. Such a rare and complex process could be a crucial factor that makes Earth unique in its ability to host advanced life forms. There have been numerous critical points in the evolutionary history of the Earth, such as the Cambrian explosion, the impact of an asteroid that wiped out the dinosaurs, and other events that could have drastically changed the course of life. It seems that Earth has been incredibly fortunate in its evolutionary journey. The rare Earth hypothesis questions how much luck has influenced the development of our planet. Many of the features that allow life on Earth and the evolutionary milestones appear to be unique or one-off events. According to the weak anthropic principle, these events could be extremely rare. We cannot assume these factors are common until we find more evidence, either by observing them on other planets or seeing them happen again. The combination of these highly improbable factors could mean that intelligent life is very rare. This could be the solution to the Fermi paradox. The galaxy could be as empty as it seems. We could, in fact, be in one of the only viable places, looking from our rare Earth towards the vast uninhabited expanse of the observable universe, which is more than 13 billion years old and incredibly vast. It contains about 2 trillion galaxies, each with billions of stars. In our own galaxy, the Via Lactea, scientists believe there are about 40 billion Earth-like planets in the habitable zones of stars. Given these immense figures, it seems unlikely that Earth is the only place where life has developed. Discovering life elsewhere would fundamentally change our vision of the universe, confirming it as a living and dynamic expanse. Such a discovery could also change our global mindset, encouraging us to look beyond our small earthly conflicts. Before looking for extraterrestrial life, we first need to clarify what exactly we are looking for. Considering the immensity and age of our universe, it is likely that different civilizations have appeared at different times, developing along unique paths and at different speeds. This means that our search for extraterrestrial life is not only about vast distances potentially spanning hundreds of thousands of light-years but also about a broad spectrum of civilizational stages, from primitive to highly advanced. To refine our search, we must develop a clear framework that helps us identify and understand these diverse forms of life in the universe. Human progress can be traced through our increasing ability to harness and use energy. We started with human muscle strength, advanced to the control of fire, and then developed the machinery to exploit the kinetic energy of water and wind. Later, through improvements in technology and materials, we accessed the dense energy stored in fossil fuels, significantly enhancing our civilizational capabilities. Based on such observations, the scientist Nikolai Kardashev developed a scale to categorize civilizations according to their energy use, known as the Kardashev scale. This scale, which has been refined over time, classifies civilizations into 4 main types, each marked by its ability to harness energy from available resources. Given that humanity is our only reference for intelligent life, we must be careful not to generalize based on our own experiences. However, we can extract some useful ideas. Human beings start with simple tools and a natural curiosity driven by competition, the need for resources, and the drive to expand. These factors have been crucial in our own development, which has led to significant technological and social advances. It seems reasonable to suggest that extraterrestrial beings capable of dominating their planet might show similar traits. In addition, if these extraterrestrials are subject to the same physical laws as us, their technological progress could be indicated by their energy consumption, a possible way to measure the advancement of alien civilizations. A Type 1 civilization, known as a planetary civilization, has harnessed all the energy available on its home planet, which includes the use of renewable sources such as solar and geothermal energy to power its industries and meet all its energy needs. They can manage and use their planet's resources efficiently. Moreover, a Type 1 civilization is not limited to its home planet, but has expanded its presence to include multiple planets and moons within its solar system. It has established a unified government that encompasses these diverse bodies, which facilitates trade, research, and interplanetary collaboration. Its technological advances have also allowed it to improve its biological capabilities and its overall technological prowess. A Type II civilization, also called a stellar civilization, can harness the energy of its entire star, which could involve building massive structures such as Dyson spheres, which completely surround the star to capture a significant portion, if not all, of its energy production. With access to the vast resources of its solar system, a Type II civilization uses this immense energy to power advanced technologies and possibly begin exploring and colonizing other star systems. A Type III civilization, known as a galactic civilization, can use the energy of its entire galaxy, which could allow it to do incredible things, like relocate planets, harness the energy of stars, power black holes, and even manipulate the structure of spacetime. Meanwhile, a Type IV civilization reaches a level of technological advancement almost unimaginable, as it would be able to create universes, suggesting its ability to operate within and possibly control multiple universes, essentially ruling a multiverse. This level of power and control transcends our current understanding of physics and technology. On the Kardashev scale, each step up represents a huge increase in energy utilization. For example, a Type II civilization harnesses 10 times more energy than a Type I, like comparing the explosive force of a nuclear bomb to the gentle punch of a small child. Humanity has not even reached the first level, but our energy consumption is undoubtedly increasing. We are currently at Type 07 on the scale. Some experts suggest that if we continue to increase our energy consumption by 3% each year, it could take between 100 and 200 years to become a Type I civilization. At that stage, we would be able to fully utilize energy like solar, wind, and hydraulic. We could control the climate and perhaps even build floating cities. These advances would significantly alter our capabilities. Imagine civilizations so advanced that they can control the energy of their entire star. These Type II civilizations could communicate using incredible technologies such as sending messages through space-time waves that allow particles to connect across vast distances. For Type III civilizations that harness the energy of entire galaxies, methods could include using wormholes or creating space tunnels that allow them to travel and communicate across galaxies almost instantly. As humanity advances towards becoming a Type I civilization, our first steps have included reaching into space to communicate with potential extraterrestrial beings. One of the first significant attempts to connect with alien life was the Voyager Golden Records. These records, a project led by Carl Sagan, were sent into space aboard the Voyager spacecraft. They included a mix of sounds, images, and music from Earth, designed to represent the diversity of life and culture on our planet. This was our way of greeting the universe and interacting with any life forms that may exist. According to the Kardashev scale, civilizations that are between Type 0 and Type I range from primitive societies to those that are about to harness the full potential of their planet, something that humanity could achieve in a few centuries. Such civilizations could be common in the Milky Way. However, without actively sending radio signals into space, even a nearby civilization, such as that of the Alpha Centauri system, could go unnoticed. Our own radio emissions, which extend up to 200 light-years, are just a small point in the immensity of the Milky Way and become indistinguishable noise after a few light-years. We have drastically changed our planet by building enormous structures, altering mountains, forests, and bodies of water, and changing the composition and temperature of the atmosphere. If we manage to keep Earth habitable, we could reach full Type I status in the coming centuries. Advancing to this level naturally leads to greater exploration and use of resources beyond Earth, driven by our inherent curiosity, competitive spirit, and tendency to expand. The journey to become a Type II civilization, one that harnesses the energy of an entire star, would involve significant advances in space technology. This path could begin with the establishment of space outposts that would then expand into more complex space infrastructures and industries over time. These advances could lead to the establishment of colonies on other planets and possibly even the terraforming of these bodies to make them more Earth-like. As a civilization's activities and consumption grow, so would its need for energy. A key milestone for a civilization transitioning to Type II would be the construction of a Dyson sphere around its star. This structure, composed of numerous individual solar satellites or other types of collectors, would capture a large portion of the energy emitted by the star, providing a nearly limitless energy source for large-scale projects throughout its solar system. With such capabilities, the ambitions of a Type II civilization could naturally expand to include reaching other star systems. This would be similar to how we currently see the challenge of traveling to Pluto, difficult but possible with enough effort and resources. Achieving this would mark the beginning of their transition towards becoming a Type III civilization, one that could utilize the energy resources of an entire galaxy. The progression towards becoming a Type III civilization, which would involve harnessing the energy of an entire galaxy, introduces complexities that are difficult for us to imagine. The challenges include not only the immense physical distances between stars, but also maintaining cultural and biological unity throughout these vast expanses. This raises critical questions. Could such a civilization overcome long travel times? Would its distant colonies remain unified, or would they travel using wormholes? As a civilization advances to Type III on the Kardashev scale, the practical challenges intensify. They may have to navigate existential risks in the interstellar void, such as cosmic radiation or unforeseen events. Imagining its form, culture, and technologies becomes increasingly speculative. Such civilizations could discover new principles of physics, harness the power of dark matter and energy, or even achieve traveling faster than light, concepts that are currently beyond our scientific understanding. Their motives, technologies, and actions could be as incomprehensible to us as a city is to an ant from the perspective of a highly advanced Type II civilization. Humanity might seem too primitive or complex for a Type III civilization. We could seem as insignificant as bacteria are to us, potentially ignoring our consciousness or survival as irrelevant. In this scenario, our best hope would be that those advanced beings were benevolent, should they ever notice us. The Kardashev scale, which classifies civilizations based on their ability to harness energy, may extend beyond what was originally proposed. Some theorists suggest the existence of Type IV and Type V civilizations that could influence entire groups of galaxies or superclusters involving thousands of galaxies and trillions of stars. At the apex of this expanded scale is the hypothetical Type Omega civilization, which could manipulate the entire universe or even create new universes. Despite the speculative nature of these classifications, they offer fascinating perspectives on the potential scale of advanced civilizations. If our theories about the capabilities of interstellar civilizations hold some truth, it seems unlikely that Type III or higher civilizations exist near the Via Láctea, since their activities would be unmistakable, marked by clear signs such as harvested stars, decaying megastructures, or evidence of large-scale interstellar conflicts. The absence of such evidence suggests that such advanced civilizations do not exist nearby. Although it may be disappointing to think that we will not be able to meet highly advanced alien civilizations, there is also a positive side. It suggests that the Via Láctea is still mostly open and available for us to explore and possibly settle in the future. This means that we have a large part of our galaxy to ourselves, without the worry of encountering a much more advanced civilization that could dominate us. The story of how the universe evolved from the Big Bang to what it is now, full of galaxies, stars and planets, connects us all from the point of view of the view. Almost 2/3 of the history of the universe had already passed before the Sun and the Earth existed. Interestingly, life on Earth may have started 44 billion years ago. This makes us wonder if life could have existed even before our planet and how far back it could go. So, when did the universe have enough heavy elements to form planets and possibly sustain life, even if we only think of life forms similar to those on Earth? The possibility of life goes back further than one might think. Right after the Big Bang, the universe had no stars, galaxies, or atoms. It began as an almost uniform mixture of matter, antimatter, and radiation. Areas with a little more matter were only 3% denser than average, which means that it would take a large gravitational collapse to form something as dense as a planet, which is much denser than the average density of the universe, but the universe had all the time necessary for this to happen. In the first second after the Big Bang, most of the matter and antimatter destroyed each other, leaving a small amount of protons, neutrons, and electrons, along with neutrinos and photons. Approximately 3 to 4 minutes later, these protons and neutrons combined to form stable atomic nuclei, but they were mostly just hydrogen and helium. It was not until about 380,000 years later, when the universe cooled enough for electrons to join these nuclei to form neutral atoms. Even then there was only hydrogen and helium, so the conditions for life or rocky planets were not yet given. Gravitational collapse is a process that changes the structure of the universe over time. It starts slowly, but it builds up. The denser a region of space becomes, the better it is at attracting more matter. Simulations suggest that the first stars could have formed around 50 to 100 million years after the Big Bang. These first stars were composed solely of hydrogen and helium and could be hundreds or even thousands of times larger than our Sun. These massive stars had a short life, of only 1 million or 2 years. When these massive stars die, it is a great event due to the fusion processes they go through. All stars convert hydrogen into helium, but the larger stars go further and fuse helium into carbon and then carbon into other elements such as oxygen, neon, magnesium, silicon and sulfur, and so on until they reach iron, nickel and cobalt. At this point, the core collapses, causing a supernova explosion that scatters heavy elements throughout the universe, enriching the space between the stars and setting the stage for the formation of rocky planets and organic molecules. As more stars live, burn, and explode, the next generation of stars becomes richer in heavy elements. Many supernovas give rise to neutron stars, and when these neutron stars collide they produce even heavier elements. This process leads to the formation of dense rocky planets and increases the chances of complex organic molecules forming. We don't need the entire universe to be like our solar system. Just a few generations of stellar life cycles in dense regions are enough to create suitable conditions for life. When the universe was 1 billion years old, we see that the most distant objects with measurable heavy elements had as much carbon as our solar system. Other heavy elements accumulated even more quickly. Carbon may take longer to reach high levels because it is mainly produced in stars that do not explode, unlike the ultra-massive ones that do. While rocky planets don't specifically need carbon, other heavy elements suffice. Phosphorus, for example, is also created in supernovas, despite recent exaggerated reports of its scarcity. Rocky planets likely began to form around the most element-rich stars when the universe was between 300 and 500 million years old. If carbon was not essential for life as we know it, life could have begun even earlier. However, for life forms like ours, a sufficient amount of carbon was probably not available until the universe was between 1 and 15 billion years old, that is, about 10% of its current age, which is later than 3 to 4% of its current age, necessary for rocky planets to form. It is fascinating to think that the universe had all the elements necessary for life, except carbon, which needed the life cycles of the most massive stars, similar to our Sun. By looking at the history of the Earth and the complexity of genomes over time, we find that the simplest life forms could go back 9 or 10 billion years instead of 12 or 13 billion years ago. Could this mean that life on Earth originated before the planet itself, or that life could have started billions of years earlier elsewhere, but took longer to develop here? We cannot say for sure. We also do not know the border between life and non-life, nor if life on Earth originated here, on another planet or even in the depths of interstellar space without a planet. So, how long ago did life arise in the universe? Although we cannot specify an exact moment, we know that for billions of years the universe has had the ingredients and conditions necessary for life. The journey from simple hydrogen and helium atoms to complex life forms is a testament to the incredible processes occurring in the cosmos. The search for life beyond Earth continues, and with each discovery, we get closer to understanding the origins and prevalence of life in the universe. It is essential to consider the factors that would have influenced life's early appearance. A significant factor is the role of supernovas in dispersing heavy elements necessary for life as we know it. These stellar explosions not only enrich the interstellar medium with elements such as carbon, oxygen, and nitrogen, but also create shock waves that can trigger the formation of new stars and planets. These newly formed stars, with their surrounding planetary systems rich in heavy elements, provide the right conditions for the development of complex chemistry. In addition to supernovas, the collision and fusion of neutron stars play a crucial role in creating even heavier elements, like gold and platinum. These events, although infrequent, contribute significantly to the diversity of elements available in the universe. The presence of these elements in the planets that formed early on would have provided a fertile ground for the appearance of life, allowing the development of complex molecules and potentially primitive life forms. The early universe was a dynamic and evolving environment, with the first stars, known as population 3 stars, forming from primordial hydrogen and helium. These stars were incredibly massive and short-lived, burning their fuel quickly and ending their lives in supernova explosions. The remains of these stars seeded the next generation of stars, known as population 2, with heavier elements. Over time, this process continued, leading to the formation of population 1 stars, like our Sun, which have a higher metallicity and are more conducive to the formation of rocky planets. The chronology of element formation is crucial to understanding when life could have first emerged. For example, elements such as carbon and oxygen, essential for life, are produced in significant quantities only after several generations of star formation and supernovas. This means that the first life forms in the universe probably had to wait until sufficient amounts of these elements were available. While rocky planets may have formed relatively early, the complexity of life we see on Earth requires a longer period for the accumulation of the necessary elements. In addition, the environments in which these early life forms could have developed are varied. It is possible that life could have begun in the depths of interstellar space, within dense molecular clouds where complex organic molecules are known to form. These clouds, enriched by the heavy elements of previous generations of stars, could have provided the right conditions for the first life forms to appear. Alternatively, life could have originated on the surfaces of early forming rocky planets, in environments such as hydrothermal vents or shallow warm pools where the combination of water, heat, and organic molecules could have fostered the development of life. Another intriguing possibility is that life could have spread throughout the universe through panspermia, the hypothesis that life exists throughout the universe distributed by meteorites, asteroids, comets, planetoids, and potentially by spacecraft in the form of unintentional contamination by microorganisms. This theory suggests that life may not have originated on Earth, but may have been transported here from elsewhere in the universe. If this were true, it would mean that life could have appeared as soon as the first habitable environments formed, potentially billions of years earlier than we currently believe. When considering these possibilities, it is also essential to reflect on the role of water in life's emergence. Water is a fundamental solvent for life as we know it, as it allows the chemical reactions necessary for life to occur. The early universe likely contained water in the form of ice, which could be found in comets and icy bodies. When these icy bodies collided with rocky planets, they were able to bring water to the surfaces, creating environments where life could develop. The presence of water in the early universe is supported by observations of water vapor in distant galaxies and around young stars, indicating that water has been present since the early stages of cosmic history. In addition, the search for life beyond Earth has led us to discover a variety of potentially habitable environments within our own solar system. Moons like Europa and Enceladus, with their oceans hidden beneath the surface, present intriguing possibilities for life. These moons are heated by tidal forces, which could create the conditions necessary for life. If life can exist in these hostile environments, it suggests that it could have emerged in similar environments elsewhere in the universe, even in the early stages of its history. Astrobiology, the study of life in the universe, has made significant advances in understanding how it could arise and survive in extreme conditions. By studying extremophile organisms that thrive in extreme environments on Earth, scientists gain information about the potential for life in the early universe. These studies demonstrate that life is incredibly resilient and adaptable, capable of surviving in conditions that were previously thought to be inhospitable. This adaptability suggests that life could have emerged early in the history of the universe, even in environments very different from those on Earth. One of the most profound implications of life's early appearance is the possibility that advanced civilizations existed long before humanity. If life began in the universe as soon as conditions allowed, then it is conceivable that intelligent civilizations could have developed billions of years before humans appeared. These civilizations would have had enough time to evolve, develop technology, and potentially explore the cosmos. The search for extraterrestrial intelligence is driven by this possibility, seeking to detect signals or other evidence of these ancient civilizations. In conclusion, the question of how early life could have appeared in the universe is not only about the timeline of element formation and planet formation, but also about understanding the diverse environments in which life could arise, the resilience and adaptability of life, and the profound implications for the existence of advanced civilizations. The universe is a vast and dynamic place full of the ingredients for life, and as we continue to explore and discover, we are getting closer to answering this fundamental question. The history of life in the universe is a testament to the incredible processes that take place in the cosmos, from the formation of the first stars to the development of complex organisms. With each discovery, we gain a deeper appreciation of the unity of all life and of the extraordinary journey from simple atoms to. I am sure that, as a space enthusiast, you have wondered how big our universe is. To answer this question, let's begin by understanding the scale. The universe is incredibly vast, and the numbers involved are almost unimaginable. Let's begin with our home planet, Earth. Earth has a diameter of approximately 12,742 kilometers. That is big, but it is just a small point in comparison with the rest of the universe. Next, let's look at our solar system. The solar system has a diameter of about 287,660 million kilometers. This distance extends from the Sun to the outer edge of the Oort cloud, a layer of icy objects that surrounds our solar system. Even within our solar system, the distances are enormous. For example, light takes about 8 minutes and 20 seconds to travel from the Sun to the Earth, which is about 150 million kilometers. Light takes more than 5 hours to reach Pluto, which demonstrates how big our solar system is. Now let's move away from our galaxy, the Milky Way. The Milky Way is a barred spiral galaxy with a diameter of about 100,000 light-years. A light-year is the distance that light travels in a year, which is about 946 trillion kilometers, so the Milky Way is approximately 946 trillion kilometers in diameter. Our solar system is located about 27,000 light-years from the galactic center. The Milky Way contains between 100,000 and 400,000 million stars and possibly even more planets, but the Milky Way is only one of the many galaxies in the universe. Our closest galactic neighbor is the Andromeda Galaxy, which is located about 2,537 million light-years away. Andromeda has a diameter of about 220,000 light-years, which makes it more than twice as big as the Milky Way. It contains approximately 1 trillion stars. Let's take a big leap and look at the observable universe. The observable universe is the part of the universe that we can observe from the Earth. It is estimated to be about 93,000 million light-years in diameter, which is equivalent to about 880 sextillion kilometers. To put it in perspective, if the entire observable universe were reduced to the size of the Earth, our entire solar system would be smaller than an atom. That's how large it is. The observable universe is estimated to contain 2 trillion galaxies, each with hundreds of billions of stars and even more planets. It is mind-blowing to think about the vast amount of celestial objects that there are in the observable universe. There are also cosmic structures like clusters of galaxies and superclusters. The largest known structure is the Hercules Corona Borealis Great Wall, a vast cluster of galaxies of about 10,000 million light-years in diameter. We can also detect the cosmic microwave background radiation, which is the residual glow of the Big Bang. This radiation offers us a snapshot of the universe when it was only 380,000 years old and helps us to understand the size and the age of the universe, but here is the crux of the matter: the observable universe is only a small part of the entire universe. The universe could be much bigger, possibly infinite. We cannot see beyond the observable universe because the light from those distant regions has not had enough time to reach us. Some theories suggest that the entire universe could be at least 250 times larger than the observable universe. If that were true, the entire universe would be about 23 trillion light-years in diameter. The universe is also expanding. This was discovered by Edwin Hubble in the 1920s. He discovered that the galaxies move away from us and that the further away they are, the faster they move. This expansion means that the universe is getting bigger all the time. This expansion is driven by something called dark energy, which constitutes approximately 68% of the universe. Dark energy is a mysterious force that causes the universe to expand at an accelerated rate. In addition, by studying the cosmic microwave background radiation, scientists have learned a lot about the size, the age and the composition of the universe. The universe shows that it is about 13,800 million years old. So, how big is the universe? The observable universe is about 93,000 million light-years in diameter, but the universe could be much bigger, possibly infinite. It is full of billions of galaxies, each of which contains billions of stars and even more planets. The scale of the universe is truly mind-blowing. Let's consider the enormous distances between celestial objects. For example, the distance between the Earth and the Moon is about 384,000 kilometers. Although this is a relatively small distance on a cosmic scale, it is still impressive that Apollo 11 took about 3 days to travel it. This distance is tiny in comparison with the distances within our own solar system. For example, the average distance between the Earth and the Sun, known as an astronomical unit, is about 150 million kilometers. Jupiter, the largest planet in our solar system, orbits the Sun at an average distance of about 52 Australian dollars, that is, approximately 778 million kilometers. Beyond Neptune is the Kuiper Belt, a region full of icy bodies, and then the Oort cloud, which extends up to around 100,000 Australian dollars or 93 trillion kilometers, marking the limit of our solar system. When we look beyond our solar system, the distances become even more amazing. The closest star to us, Proxima Centauri, is about 424 light-years away. A light-year, the distance light travels in a year, is about 946 trillion kilometers, meaning Proxima Centauri is about 40 trillion kilometers away. Even traveling at the speed of the New Horizons spacecraft, one of the fastest man-made objects, it would take over 70,000 years to reach Proxima Centauri. If we move even further away, we reach our galaxy, the Milky Way. Our solar system is in one of the Milky Way's spiral arms, about 27,000 light-years from the galactic center. The Milky Way is part of a local group of galaxies that includes Andromeda, the Triangle Galaxy and 54 other smaller galaxies, and our nearest spiral galaxy neighbor is on a collision course with the Milky Way and is expected to merge with our galaxy in about 45 billion years, forming a new galaxy that some astronomers refer to as Mila or Andromeda. One of the most mind-blowing aspects of the universe's size is that it is not static, but constantly expanding. This expansion, discovered by Edwin Hubble in the 1920s, implies that galaxies are moving away from us, and the further away they are, the faster they move away. This observation led to the formulation of Hubble's law and the understanding that the universe began with the Big Bang. The rate of expansion measured by the Hubble constant remains a subject of research and debate among scientists. The expansion of the universe is driven by dark energy, a mysterious force that makes up approximately 68% of the universe. Unlike dark matter, which interacts with gravity and helps hold galaxies together, dark energy acts in opposition to gravity, thus causing the acceleration of the expansion of the universe. This means that the universe is not only expanding, but is doing so at an increasing rate. The exact nature of dark energy remains a greatest mystery of cosmology. How do we know the universe's age? Scientists use various methods to determine its age and size. A key idea is the Big Bang theory. This theory says the universe began as a tiny, extremely dense and hot point about 138 billion years ago. This point expanded rapidly, creating space, time, and matter. The Big Bang theory is supported by several pieces of evidence, including the observation of galaxies moving away from us, the presence of light elements, and the cosmic microwave background radiation. One of the most important pieces of evidence for determining the age of the universe is the CMB, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is the afterglow of the Big Bang. It is the leftover heat of the early universe, now cooled and stretched to microwave wavelengths. Because the universe is expanding, the CMB gives us a snapshot of the universe when it was only 380,000 years old. By studying small variations in the CMB, scientists can learn about the initial conditions of the universe and how it evolved. These variations tell us about the distribution of matter and energy in the early universe, which helps us estimate its age. The European Space Agency's Planck satellite, launched in 2009, provided the most detailed map of the CMB by analyzing Planck data. Scientists refined their estimate of the universe's age to 138 billion years. Another method for determining the age of the universe is observing its expansion. In the 1920s, astronomer Edwin Hubble discovered that galaxies are moving away from us. The further away a galaxy is, the faster it moves. This relationship is known as Hubble's law. Measuring the Hubble constant allows scientists to estimate the time elapsed since the Big Bang, giving us an estimate of the age of the universe over the years. Different methods have been used to measure the Hubble constant, including observing Cepheid stars and studying the CMB. These methods have consistently supported the Big Bang theory and estimates of the age of the universe. Stars also provide valuable clues about the age of the universe. By studying the life cycles of stars, scientists can estimate the ages of the oldest star clusters. An important type of star cluster for this purpose is globular clusters. Globular clusters are dense groups of tens of thousands to millions of stars that formed early in the universe's history. The stars in these clusters are among the oldest known, with ages estimated at around 13 billion years. By analyzing the light from these stars and comparing it to models of how stars evolve, scientists can estimate the cluster's age. Since globular clusters formed shortly after the Big Bang, their ages provide a lower limit for the universe's age. Another method for determining the age of the universe involves the radioactive decay of certain elements, such as uranium and thorium. Decay occurs at known rates, so by measuring the proportions of these elements in ancient stars and meteorites, scientists can estimate the time elapsed since they formed. This technique, called radioactive dating, has provided age estimates consistent with other methods, supporting the idea that the universe is around 138 billion years old. Gravitational waves, ripples in spacetime caused by violent cosmic events, offer another way to study the universe's history. First detected in 2015 by the LIGO and Virgo observatories. Gravitational waves provide a new way to measure the Hubble constant and the universe's age. By observing the mergers of neutron stars and black holes, scientists can use gravitational waves to estimate distances and the rate of the universe's expansion. This new field of gravitational wave cosmology promises to provide even more accurate estimates of the universe's age. According to general relativity, our universe has specific characteristics. It is uniformly dense on a large scale, has consistent laws and properties, and the Big Bang occurred everywhere at once. These characteristics create a unique link between the universe's age and its expansion history. To determine it, we rely on various observations, including direct measurements of the brightness and distance of celestial objects, which help us build the cosmic distance ladder. We also use observations of large-scale structures, baryon acoustic oscillations, and fluctuations in the cosmic microwave background, which offers a snapshot of the universe when it was only 380,000 years old. To summarize the age of the universe, scientists use several methods, including the study of the cosmic microwave background, the observation of redshifts of distant galaxies, the analysis of the life cycles of stars in globular clusters, and the exploration of the effects of dark matter and dark music. For years, human beings have always asked themselves a question: what shape does the Earth have? Is it flat, round, rectangular, or like a saddle? As of today, we know that our Earth is approximately a sphere. However, have you ever considered the shape of the universe? As scientists have discovered, the universe is expanding infinitely and is not slowing down, but its shape is still a matter of debate. There are three possible shapes: flat like paper, round like a ball, or saddle-shaped, like a horse's saddle. These shapes are not just theoretical ideas, but have significant implications for the future of the universe. They can tell us a lot about its past and what could happen next. Will the universe continue to expand forever? Will it begin to contract, or is it infinite and unlimited? Let's explore what these different shapes mean for the destiny of the music cosmos. The general shape of the universe depends on two main factors, its density and its expansion speed. So, is the universe closed, open, or flat? Approximately 2/3 of a universe is made up of dark energy, and just over a quarter is dark matter, the rest is the normal matter we know, such as planets and stars. When scientists talk about the density of the universe, they are referring to the amount of matter and energy in space. If the universe has enough density for gravity to balance its expansion, it will take a spherical shape known as a closed universe. A closed universe would be finite, but without limits, which means that one could travel endlessly without ever reaching an edge. On the other hand, if the universe does not have enough density to stop its expansion, it will be saddle-shaped, known as an open universe. However, the most reliable scientific data suggests that the universe is flat. In a flat universe, the density is adequate, allowing it to expand in all directions without curvature. What does it mean for the universe to be flat? This flatness is not like a two-dimensional surface that we see every day. Instead, imagine that you are in a corner of a square room, walk 3 meters to the next corner along the wall, then turn 90 degrees, walk another 3 meters, turn another 90 degrees and do this 2 more times, you will end up back where you started, forming a square. This follows the Euclidean geometry that we learned in school. Now, if we add an extra dimension to this concept, we get a flat universe. Let us now consider a universe with positive or closed curvature. Let's imagine that we start from the equator of the Earth and walk towards the North Pole. Let's imagine that we start from the equator of the Earth, walk towards the North Pole, turn 90 degrees, walk back to the equator, turn another 90 degrees and return to the starting point. In a flat universe, you would need 4 turns to return to the starting point, but in a closed universe you would only need 3. To simplify it even more, imagine 2 rockets flying side by side in a flat universe. They would remain parallel forever. In a closed universe, their trajectories would end up curving and meeting again. In an open universe, they would move away and never meet. An important clue about the shape of the universe comes from the cosmic microwave background, which is residual heat from the Big Bang. Scientists have studied the temperature variation in the CMB and have found almost no curvature to support the idea of a flat universe. However, in 2019, a study suggested that CMB measurements could indicate a closed universe. This was based on the curvature of light from the CMB due to gravity. The amount of curvature observed was greater than expected, and a closed universe could explain this, but the team that performed the measurements did not think it was a big deal. Some experts believe that it could simply be a random anomaly in the data. Even so, these findings are noteworthy. They do not directly prove that the universe is closed, but suggest that something important could be happening. Some researchers even call it a cosmological crisis. If the universe were closed, it would conflict with other data, making it difficult to accept if proven true. The idea of a closed universe would overturn years of consolidated research. However, there is no other evidence that challenges the prevailing view that the universe is flat. Other CMB measurements and telescope data support a flat universe. Additional data, such as the patterns left in the galaxies by ancient sound waves, also support the flatness hypothesis, given the overwhelming evidence in favor of a flat universe. Most scientists remain skeptical of a single contradictory finding. While the study suggesting a closed universe is interesting, other data consistently support a flat universe. Recent research combining multiple data sets found no deviations from flatness, suggesting that the observed anomaly could be a statistical fluctuation. Other studies have reached similar conclusions, indicating that there is no need to revise the current cosmological model. For now, it seems that the universe behaves like a 3-dimensional sheet of paper, although not everyone is totally convinced that it is flat. That is how it seems based on current observations. It is important to remember that our vision is limited to the observable universe, so there could be aspects of which we are unaware. If the universe has curvature, it would have to be so immense that the 93,000 million light-years that we can observe are not enough to detect it. To make an analogy, it is like being in a field with fog and only being able to see a small flat area while the true shape of the terrain remains hidden by the fog. When we say that the universe is flat, we mean that the part we can observe looks like a flat three-dimensional space. Galaxies are enormous collections of stars scattered throughout the universe, and counting them is a difficult task for several reasons. First, there are billions of galaxies, which makes counting them all a monumental effort. Secondly, our telescopes have limitations. They must be large and located in space to avoid the blurring effects from the Earth's atmosphere. For the best results, a good example of these challenges is the extreme deep field image created from 10 years of photos taken by the Hubble Space Telescope. This image was made by observing a small part of the sky for 50 days to understand just how small this area is. Imagine holding a pinhead up in the sky with your arm extended. Even in this tiny spot, the XDF revealed thousands of galaxies at different distances, providing one of the deepest views of the universe at the time. Since thousands of galaxies are found in such a small area, scientists estimate that there are between 100 billion and 200 billion galaxies throughout the universe. New, more advanced space telescopes are expected to help us learn even more about the earliest galaxies. The Hubble Space Telescope, which produced the XDF, has played an important role in estimating the number of galaxies. It was launched with a defective main mirror but was subsequently repaired and improved several times. In one study, the telescope was pointed at what appeared to be an empty part of the sky for 10 days, revealing an image with about 3,000 faint galaxies. With new improvements, more detailed studies became possible. One study produced an image called the ultra-deep field, which showed about 10,000 galaxies in a small area of sky. Another study that used better instruments, focused on a part of the ultra-deep field and found about 5,500 galaxies in an even smaller area. Now, with this understanding of the enormous number of galaxies in the universe, let's delve into a question that often baffles many: if the universe is expanding, where is its center? To answer this, we first have to understand what we mean by expanding. Imagine inflating a balloon. As the balloon inflates, all the points on its surface move away from all other points. Similarly, as the universe expands, each galaxy moves away from all the others. Here is the interesting part of this balloon analogy: there is no single center on the surface of the balloon, all points move away from all others, so from the perspective of any galaxy, it seems that it is at the center of the expansion. This means that there is no central point in the universe from which everything expands, but rather that expansion occurs uniformly everywhere. It's like baking raisin bread. As the dough rises, all the raisins move away from each other, but there isn't a specific raisin in the center that all the others move away from. Therefore, when we say that the universe is expanding, we are talking about an increase in the distance between galaxies, not an expansion from a specific central point. This expansion is a key test of the Big Bang theory, which postulates that the universe began as a hot, dense point and has been expanding ever since. Now you will ask yourself, if there is no center of expansion, where does this leave us in the universe? Are we at a special point? The answer is no. Observations show that the universe looks more or less the same in all directions, a concept known as isotropy. This suggests that, regardless of where you are in the universe, it will appear that you are at the center of expansion. This leads us to the idea of homogeneity, which means that, on a large scale, the universe is the same everywhere. These concepts of isotropy and homogeneity are fundamental to our current understanding of cosmology and support the idea that there is no special location or center of the universe. So the next time you look at the night sky and marvel at the countless galaxies, remember that each one moves away from the others and that there is no center in this great cosmic dance. The universe is expanding everywhere at once, without a single point as the origin of this expansion. Think of the composition of the universe as the portions of a pie chart, each representing a different component. First, we have normal matter, which is only 5% of the universe, including the atoms that make up the stars, planets, and everything we see around us. Next is dark matter, an unknown fundamental particle that accounts for about 25% of the universe. Scientists calculate the amount of dark matter by observing small temperature variations in the cosmic microwave background. These calculations match what we observe in the movements of stars and galaxies. The CMB comes from an era when the universe had cooled enough to release the photons from the hot plasma that trapped them for hundreds of thousands of years after the Big Bang, confirming that dark matter was present in the early universe. Atoms or normal matter constitute only 1/16 of the total mass of the universe. Then there is dark energy, a mysterious force responsible for the rapid expansion of the universe. It constitutes 70% of the total matter and energy of the universe. We also have the optical layer, which tells us how much light the universe absorbs and scatters, in particular photons. This layer helps us understand the complex processes behind the birth and explosive end of the first stars and the formation of the earliest galaxies. When these first stars and galaxies formed, they emitted intense radiation that broke hydrogen atoms into protons and electrons. This event, known as reionization, caused between 5 and 8% of the CMB photons released during the era of decoupling to scatter once again. Imagine it as a light fog that appears in a previously clear universe, slightly reducing our visibility. To measure this optical depth of the universe, scientists study the polarization of the CMB, which gives us clues about the early stages of the universe and helps us to reconstruct the history of how the first stars and galaxies arose. When exploring the mysteries of the universe, we find ourselves with the concept of polarization, which together with the intensity and the wavelength is one of the three attributes of a light wave. Some of the fluctuations and the formation of structures in the universe are described by the primordial power spectrum, which describes the variations in the density of the universe through three-dimensional space. In the early universe, these fluctuations were smaller, but as the universe expanded, these variations in density were magnified. The scalar spectral index provides information about the origins of the universe by informing us how these initial fluctuations evolved over time. Using these 6 parameters, we can calculate not only the properties of the CMB, but also other cosmological measurements. For example, we can determine that the age of the universe is 138 billion years, with an error margin of 40 million years. The most restrictive observation comes from the CMB's anisotropy, which shows subtle temperature variations. The standard cosmological model fits well with all observations from diverse scientific disciplines, including physics and astronomy. One of the most important tools for studying the universe is the telescope. From the first telescopes to modern ones, telescopes allow us to observe distant objects in space, from planets and stars to galaxies and nebulae. There are different types of telescopes designed to observe different wavelengths of light, from visible light to radio waves and even X-rays. Optical telescopes, such as the famous Hubble Space Telescope, capture light in the visible spectrum and provide impressive images of distant galaxies and nebulae. Radio telescopes, such as the Arecibo Observatory, detect radio waves emitted by celestial objects, helping us to study phenomena such as pulsars and black holes. X-ray telescopes, such as the Chandra X-ray Observatory, observe high-energy events such as supernovas and the regions around black holes. In addition to telescopes, scientists have launched numerous space missions, space probes and satellites that travel beyond the Earth's atmosphere, providing a clearer view of the cosmos without the interference of for example, the Voyager probes launched in the 1970s have traveled beyond our solar system sending data about the outer planets and the interstellar medium. The New Horizons mission provided us with our first close-up images of Pluto and continues exploring the Kuiper Belt. In addition, the most advanced telescope, the James Webb Space Telescope, helps study exoplanets and various celestial bodies. One of the key methods to study the universe as a whole is to examine the cosmic microwave background, CMB, for its acronym in English. The CMB is the residual glow of the Big Bang, a faint radiation that fills the entire universe and provides an image of the cosmos when it was only 380,000 years old. By studying the CMB, scientists can learn about the early conditions of the universe, its composition, and its age. The Planck satellite provided the most detailed map of the CMB, revealing small fluctuations that tell us about the distribution of matter and energy in the early universe. In addition, scientists carry out large-scale surveys of galaxies. These studies map the positions and properties of millions of galaxies, revealing the cosmic web, a vast network of galaxies and dark matter that extends throughout the universe. The Sloan Digital Sky Survey is one of the most comprehensive galaxy studies, mapping millions of galaxies and helping us understand the large-scale structure of the universe, its expansion, and the distribution of dark matter. Considering the immensity of the universe, it is intriguing to reflect on our significance within it. Are we unique in the cosmic scheme, or just one of numerous life forms potentially scattered throughout the cosmos? This leads us to the question, was the universe specifically designed with us in mind? This idea is summarized in the anthropic principle, which suggests that the fundamental laws and constants of the universe appear to be meticulously calibrated to sustain life, especially intelligent life such as that of human beings. For example, the precise values of the force of gravity, of electromagnetic interactions, and the characteristics of atoms are essential for life. Any slight variation in these constants could make life impossible as we know it. So, does this precision in the design of the universe suggest that it was created specifically for us? Some argue that the exact conditions that allow life are too precise to be a mere coincidence, suggesting intentional creation. On the contrary, others argue that this fine-tuning is simply the result of natural processes and chance. They point out that in an immensely vast universe, it is entirely plausible that at least one planet like Earth has naturally developed the perfect conditions for life. The multiverse theory adds another layer to this debate by proposing that our universe is only one among potentially countless others, each governed by its own set of physical laws and constants. In this vast multiverse, only a few universes could harbor conditions conducive to life. If this theory is true, our universe is not particularly special, it is simply one of the few where conditions align perfectly for life, making the concept of fine-tuning less extraordinary. The exploration of extraterrestrial life also influences this debate. The discovery of life beyond Earth, whether microbial life on Mars, in the hidden oceans of moons like Europa and Enceladus, or in distant exoplanets, would imply that life is not an exclusive phenomenon of Earth, but exists anywhere where conditions are favorable. Such discoveries could drastically change our understanding of the rarity of life in the universe, beyond the scientific realm. Philosophical opinions also shape our understanding of the universe. Some find comfort in believing that the universe has a deliberate purpose, while others appreciate the beauty of its randomness and infinite possibilities. Regardless of the universe's intention, our innate curiosity and drive to explore are quintessential human traits. Delving into these profound questions not only drives scientific advancement, but also deepens our understanding of the cosmos. Science shows us a vast and seemingly indifferent universe, which can make us feel insignificant, but some argue that we could still occupy a central role in the cosmos due to the finely tuned laws of physics that make life possible. For example, the specific force is vital for stars to produce carbon, a fundamental component of life. Even the energy in the vacuum of space appears calibrated for the emergence of intelligent life. This apparent tuning has given rise to various interpretations of the anthropic principle. One perspective postulates that the universe was deliberately designed with us in mind, possibly by an intelligent entity. Another concept, the principle of life, suggests that life is an inherent characteristic of the universe. However, these opinions are not widely supported in the scientific community. An alternative philosophical interpretation of the anthropic principle is that the universe exists because we are here to observe it. A more pragmatic view maintains that the universe seems tailor-made for our existence simply because we live in a region that supports life. This could be explained by the existence of multiple universes, each governed by different physical laws, ours being one of the few capable of harboring life. About 1,375 billion years ago, the universe came into existence, and shortly after the first light began to propagate through the cosmos, marking the first stages of the expansion of the universe. Initially, this expansion occurred rapidly, but shortly after it slowed down. However, under the influence of dark energy, the rate of expansion has accelerated over time. In essence, the universe has been expanding faster since its inception. Cosmologists estimate that the oldest photons we can observe have traveled between 45 billion and 47 billion light-years since the Big Bang, which suggests that the diameter of the observable universe is about 93 billion light-years, more or less. This observable universe includes everything we can see, from the smallest particles, such as quarks, to the largest structures, such as quasars, stars, planets, nebulae, and black holes. It is important to note that the observable universe is limited to the light that has reached us, but how can the observable universe be 93 billion light-years in diameter if the universe itself is only about 138 billion years old? This apparent contradiction is resolved by understanding a fundamental concept of physics. According to the theory of special relativity, objects close to each other cannot exceed the speed of light between them. However, this limit does not apply to distant objects, especially when the space between them expands. It is not that these objects move through space faster than light, but that space itself expands, causing them to move away from each other at great speeds. To reach the edge of the observable universe, it would be necessary to overcome the speed of light, a feat considered impossible by most physicists, or find a way to circumvent the limitations of spacetime, perhaps through theoretical constructs such as wormholes or warp drives, although both options are considered highly speculative. According to the concept of cosmic inflation, the universe could be at least 10 to the power of 23 times larger than we can observe. What lies beyond the observable universe remains a mystery, as it falls outside our ability to observe. However, several theories speculate about what could exist in these unexplored regions. The first theory is simple but surprising. Astronomers think that the space beyond what we can see could simply be a continuous extension of cosmic characteristics similar to those of our observable universe. It makes sense to assume that the universe beyond our location would not be radically different from what we can observe. It is difficult to imagine a universe that simply ends abruptly, as if there were a giant wall marking its limit, so the idea that the universe could be infinite is natural. But infinite means that beyond what we see there could be infinite stars, planets, and even all the possible scenarios you can imagine. If the universe were truly infinite, following this idea to its ultimate consequences, it means that somewhere out there could be another person who looks exactly like you and lives a life remarkably similar to yours. There could also be versions of you that are slightly different, perhaps one is a little shorter, another could have passed away a few years ago, or another could be missing a finger. It is possible that this other version of you is watching this video right now, maybe even picking their nose like you would be doing, or maybe not. It is a far-fetched idea, but that is how the concept of infinity works. Another theory called dark flow emerged in 2008 when astronomers observed clusters of galaxies moving in the same direction at an incredible speed of more than 2 million miles per hour. This could be caused by huge unknown structures beyond what we can see that pull on these galaxies with their gravity. These structures could be huge clusters of matter and energy or unusual distortions of spacetime that could even connect to other universes. We really do not know what these massive entities could be, although some recent studies have tried to discredit the theory of dark flow. It is still being debated. There is also the idea of a multiverse, in which our universe is just one bubble in a huge sea of other universes. This theory suggests that these universes can interact, and the gravitational pull between them could cause collisions that could lead to events similar to our own Big Bang. These ideas are just some of the popular theories about what could be beyond the part of the universe that we can see. The true nature of what is out there remains one of the greatest mysteries of cosmology, which drives continuous research and discovery to learn more about our vast universe. Some theories even suggest the existence of additional dimensions beyond the three spatial and temporal dimensions that we experience daily. For example, string theory proposes additional dimensions that are too small for us to detect. If these additional dimensions exist, they could contain entire universes with their own sets of physical laws and constants, which could offer information about the structure and limits of our universe. There is also the theory of the cyclic universe, which suggests that the universe goes through infinite cycles of expansion and contraction. According to this theory, the universe expands to a certain point, then gravity pulls everything back into a dense state, leading to a big crunch that triggers another Big Bang. This continuous cycle of creation and destruction suggests that the edge of the universe could be just a transition point in an eternal sequence. In addition, some scientists propose the concept of a cosmic horizon, a limit beyond which we cannot see or interact. This horizon represents the farthest distance that light has traveled to us since the universe began. Everything beyond this horizon remains out of our reach, locked by the finite speed of light and the age of the universe. As we delve into the cosmos with more sophisticated technology, each discovery brings us closer to understanding these profound mysteries, whether through advanced telescopes, cutting-edge theoretical physics, or innovative space missions. Our journey to understand the limits of the universe continues. The edge of the universe, vast and seemingly limitless, contains regions that are forever unattainable due to our technological limitations and the nature of cosmic expansion. So, what parts of the universe are really accessible to us, and how far can we realistically expect to explore? So, what parts of the universe are really accessible to us and how far can we realistically expect to reach? When we look at the night sky, it may seem eternal, but the stars have their life cycles and these do not last indefinitely. Let us consider the Milky Way, which extends up to 200,000 light-years and houses between 100 billion and 41 trillion stars. Surprisingly, only about 3 new stars are formed per year, which means that 95% of all the stars that will exist have already been formed, and we are now in a period of decline in star formation. As this rate decreases, we are approaching what could be considered the twilight of the stellar era of the universe. In addition, the universe itself continues to expand. Moving away from us, the Milky Way is part of a larger set known as the Local Group, which includes the Andromeda Galaxy and more than 50 dwarf galaxies covering about 10 million light-years. This group is only part of the Laniakea supercluster, which is located among countless superclusters. In total, the observable universe houses about 2 trillion galaxies. However, even if we could travel at the speed of light, about 94% of the galaxies we can see today will always be out of our reach. This harsh reality stems from the same event that formed these galaxies, the Big Bang. In simpler terms, shortly after the Big Bang, the universe was a small, dense bubble of energy. Even small variations in density at this stage had monumental consequences during the phase known as cosmic inflation, as the universe expanded from the size of a marble to trillions of kilometers wide in less than a second. This explosive expansion amplified these tiny density differences to galactic scales, which led to the formation of variable densities throughout space. Once inflation ceased, gravity began to attract matter, leading to the development of groups of galaxies such as our local group, but beyond these dense regions, the universe continues to expand. The local group is surrounded by other structures that are not gravitationally bound to it and move away as the universe expands, which increases its complexity. This expansion not only continues, but accelerates, driven by what we currently call dark energy. The simple fact of understanding that the universe is expanding faster gives us an idea of the challenges that cosmic exploration poses. This acceleration creates a kind of border around us known as the cosmological horizon. Everything beyond this border moves away from us faster than the speed of light, making it permanently unattainable. This is similar to the limit that surrounds a black hole, known as the event horizon, except that it surrounds us all. 94% of the galaxies we can currently see have crossed this limit and are moving away from us forever. You may wonder how we can still see these galaxies if they are unattainable. It is because light travels through time, and we are seeing the light from these galaxies as it was when they were closer to us. This means that the visible universe is larger than the part we can actually visit or interact with. Essentially, the universe shows us galaxies that we will never be able to visit. We cannot know what they are like now, but their ancient light will continue to reach us for a long time. Over time, all the structures outside our local group will cross this border, and we will no longer be able to see them. However, around 6% of the observable universe is still within our reach, composed of groups of galaxies less than 18 billion light-years away. Although they are also moving away, they are doing so slowly enough to remain accessible for now, even though this opportunity is diminishing. Even a very advanced civilization would have a lot of difficulty reaching these groups. For example, it would take 11 million years at the speed of light to reach the Maffei group, the closest group of galaxies outside our own local group. Given our current technology, it is very unlikely that humans will ever travel beyond the local group. This group of galaxies is probably the largest cosmic structure we will ever explore, Even traveling between stars within the local group would be an enormous feat. Simply colonizing this small part of the universe would be a significant achievement, as it only represents a small part of everything we can observe, as dark energy continues to influence the universe's expansion. The galaxies within the local group will be increasingly bound by gravity, and, over time, these galaxies will merge into a single large elliptical galaxy that has been provisionally named Andromeda. This merger, which will take place within a few billion years, is expected to even trigger a brief period of new star formation. However, the galaxies outside of Andromeda will eventually move too far away to be seen. At that time, we will no longer receive any information from beyond the local group. In the distant future, any being living in Andromeda might believe that their galaxy is the entire universe. Looking into space, they will only see emptiness. They will know nothing of the cosmic background radiation or the Big Bang and may assume that the universe is static and unchanging. Andromeda will be like a dark and isolated island in the universe. However, with its trillions of stars, the local group offers a vast space for humanity to explore for many years to come. We have not yet left our solar system, and we have billions of years to explore our galaxy. We are lucky to live in an age where we can still observe both our future and our distant past. We currently live in a world with 3 dimensions, including up and down, left and right, and forward and backward. These are the directions in which we can move. Time is another dimension that we experience as we move from the past to the future. Together, these 2 concepts make up what we call spacetime in physics. Dimensions are like different directions in which you can move. You can think of them as the lines on a graph. Normally, we only experience 3 dimensions, but what if there are more dimensions that we cannot see? Theories such as string theory and M-theory from the world of theoretical physics suggest that there could be additional dimensions. According to string theory, the smallest parts of our universe are not points, but small vibrating loops of energy called strings. The mathematics behind string theory suggests that it is necessary for there to be 10 or 11 dimensions for everything to work. String theory attempts to explain all the forces of nature, gravity, electromagnetism, and nuclear forces, saying that everything is composed of these strings. The different ways in which strings vibrate give rise to different particles. Why don't we see these additional dimensions? They could be incredibly small and very folded, making them impossible to detect with our current tools. For example, imagine an ant on a tightrope. For the ant, the rope looks like a line because it cannot see the width. In the same way, these extra dimensions exist, but are too small or hidden for us to notice them. If these superior dimensions exist, they could help us understand some of the most important questions of physics, such as why gravity is much weaker in comparison with other forces. Perhaps gravity extends into these extra dimensions, which would explain why it seems weaker in our 3-dimensional world. The extra dimensions could help us better understand the basic nature of forces and particles. They could unite all the natural forces in a great framework that could lead to new technologies and a deeper knowledge of the universe. Scientists are trying to find evidence of these extra dimensions. One way to do it is to look for small changes in gravity's behavior at very small scales. If the extra dimensions are real, they could cause slight unusual effects in the functioning of gravity that we could detect in laboratory experiments. Another method consists of using collisions of high-energy particles, such as those in the Large Hadron Collider. These experiments collide particles at high speeds, and if some particle disappears into extra dimensions, it could indicate that these dimensions exist. There are also other interesting ideas about the extra dimensions. For example, some theories suggest that our universe could be a 3-dimensional brain floating in a space with more dimensions. In this idea of a brain world, our universe could be only one of many parallel universes, each existing as a separate brain in a space with more dimensions. This raises exciting possibilities about how these universes could affect each other, such as through gravity or the exchange of particles. Another idea related to the extra dimensions is the theory of the multiverse. This theory suggests that our universe is just a bubble in a vast array of other universes, each in an extra-dimensional space. These different universes could have their own sets of physical rules and could even interact with each other. For example, when these universes collide, they could create an enormous explosion similar to the Big Bang that gave start to our universe. Although the concept of extra dimensions is fascinating, it is still only a theory. One of the biggest obstacles is that these dimensions are not something we can see or measure directly at present. To detect them, we would need extremely high energy levels or very precise measurements beyond our current capabilities. Mathematics is essential to helping us understand the concept of extra dimensions. Many theories that suggest the existence of these additional dimensions depend to a great extent on complex mathematical ideas of geometry, topology, and algebra. These branches of mathematics help us imagine and make sense of spaces that go beyond our usual three-dimensional understanding. Mathematicians and physicists collaborate to create models that hypothesize how these extra dimensions could affect what we observe in the universe. These models are put to the test through various experiments and observations. Quantum mechanics, which studies how things are on incredibly small scales, could also be affected by the extra dimensions. The strange and often disconcerting behaviors we see in quantum mechanics could be due to interactions taking place in spaces with more than 3 dimensions. So, do extra dimensions really exist in the universe? Although we still do not have solid evidence, the possibility that extra dimensions exist is an exciting and active field of research in theoretical physics. If these dimensions exist, they could drastically change our understanding of the universe and reveal new secrets about the nature of reality. As we continue to immerse ourselves in these intriguing ideas, who knows what we might discover? The universe is full of mysteries.